Look at the world around you. Your screen, the room you're in, the ground beneath your feet. They all seem perfectly still. This feeling of stability, of quiet immobility, is the foundation of our experience, the silent stage on which our stories unfold. We trust this stillness. We rely on it, but it turns out this trust is misplaced. This stillness is an illusion. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. It's a simplified user interface for reality, one our senses perfected over millions of years of evolution because the truth is far stranger. Right now, you are part of a storm of motion so extreme and so constant it governs everything, from the smallest imaginable particles to the largest structures in the cosmos. The atoms in the very chair you're sitting on are vibrating with almost unimaginable speed. The electrons inside them aren't solid points, but a blurry cloud of pure probability. And you, that chair, and this planet are all hurtling through the darkness of space at over 1,000,000 miles per hour. So, if nothing is ever truly still, what is this reality we experience? And why do our own minds work so hard to hide the truth? To figure that out, we need to go on a journey. A journey of scale, from the quiet theater of your own mind, down into the chaotic world of the atom, and out into the silent dance of the universe. Let's start this journey not with physics, but with you. Right here, right now. Take a moment. Feel the stillness. If you're sitting, your body feels at rest. You might even try to quiet your mind. In these moments, we feel like we're approaching a state of true zero. Perfect stillness. But what's actually happening inside your brain when you feel this calm? You might think you're turning everything off, but the truth is far more active. Your brain isn't just shutting down, it is actively and precisely editing your perception. It is building the illusion of stillness for you, in real time. And the way it does this reveals the first crack in the facade of a stationary world. To understand this, we need to meet a part of your brain called the Orientation Association Area, or OAA. Located toward the back and top of your head, the OAA has a critical job. It constantly builds your sense of self in space. It's the silent navigator that tells you where your body ends and the world begins, letting you walk through a doorway without bumping into the frame. It does this by taking a flood of sensory information and integrating it into a coherent map of you. But what happens when you decide to be still? When you sit down to meditate, you begin to systematically starve the OAA of new information. The sensory input, the feeling of your feet on the floor, the sight of the room, all quiets down. Neuroscientists Dr. Andrew Newberg and Eugene Dockweilie wanted to see what was happening in the brain during this process. Using scans that measure blood flow, they studied the brains of monks and nuns during deep meditation. What they found was astonishing. As the practitioners entered states they described as timeless and boundless, the activity in their Orientation Association area plummeted. The more the part of their brain for focused attention lit up, the more the OAA went dark. Think about what this means. Your brain isn't just passively experiencing stillness. It's actively creating it by powering down the very module that defines your physical boundaries. When the OAA stops drawing that sharp line between you and the world, you can feel a sense of oneness, of dissolving into your surroundings. Your brain literally stops tracking your body in space, and in doing so, constructs a powerful sensation of absolute stillness. It's a manufactured experience. While your mind feels at peace, your body is anything but still. Your heart beats, your lungs expand, and trillions of cellular processes churn away. Your brain is just choosing to filter out this constant, roiling sea of internal motion. There are incredible stories, some more legend than verified fact, that hint at the extremes of this control. One famous, though scientifically unverified, Account tells of an Indian yogi named Satyamurti, who was reportedly monitored while being confined to a sealed pit for 8 days. The story claims that after an initial spike, his ECG flatlined for nearly 7 days, showing no detectable heart activity, yet he emerged alive and well. While this event contradicts known human physiology, complete cardiac arrest for that long would cause irreversible damage. It speaks to a long-held fascination with the mind's power to influence the body's supposedly automatic functions. It's an extreme example, but it underscores a fundamental point. What we perceive as stillness is often a state of profound biological control. Our brain creates a user interface, a clean desktop view of the world that hides the messy code running underneath. It gives us the illusion of stillness because, on a practical level, that's what we need to function. You don't need to account for a glass of water being made of vibrating atoms hurtling through space. You just need to know it's asterisk there, and it's still. But it's not. And to see why, we need to leave the world of perception and begin a journey inward. Let's return to the chair you're sitting on. It feels solid, still, but this is an illusion of scale. If we were to zoom in, we would enter a world of perpetual, violent motion. The first layer is thermal vibration. Every object with a temperature above absolute zero is brimming with energy that manifests as the constant, frenetic vibration of its atoms. They are shaking back and forth like a trillion tiny bells, all ringing at once but making no sound. The frequencies are staggering, on the order of trillions of times per second. To put that in perspective, the blur of a hummingbird's wings, beating about 50 times per second, is almost perfectly still by comparison. In the air around you, it's even more chaotic. Nitrogen and oxygen molecules are careening through space at hundreds of meters per second, faster than the speed of sound. The steady air pressure you feel is the averaged-out result of this unceasing, high-speed bombardment against your skin. But what if we could remove all that heat? What if we could cool your chair down to absolute zero? Minus 273.15 degrees Celsius. Surely then, the atoms would finally be still. Right? Wrong. And this is where we leave familiar physics and enter the bizarre world of quantum mechanics. According to the Heisenberg uncertainty principle, we cannot know both a particle's exact position and its exact motion at the same time. For an atom to be truly still, it would need a perfectly defined position and a perfectly defined momentum of zero. This would violate the uncertainty principle. It's a physical impossibility. Therefore, even at absolute zero, particles must retain a minimum amount of motion. This is called *0-point energy. It is the fundamental, irreducible quantum jitter woven into the fabric of reality. Liquid helium is a stunning real-world example of this. At normal atmospheric pressure, it refuses to freeze, no matter how cold it gets. Even as it approaches absolute zero, its atoms have too much zero-point energy, too much quantum jitter, to ever lock into the stable structure of a solid, though it can be forced to solidify under immense pressure. Stillness is, quite literally, forbidden by the laws of physics. We can go deeper. An atom is mostly empty space, with a nucleus at the center and electrons orbiting it. But the model of electrons as tiny planets is wrong. An electron in an atom isn't a solid point, it exists as a probability cloud. Think of a blurred photograph of a fan blade. The blade is moving too fast to be pinned down, so it appears as a blurry disk. The electron's existence is like that, but more fundamental. It's not just moving too fast to see, it is a smear of potential, a wave of probability. The very concept of a static, pinpoint location dissolves at this scale. And what about the empty space between the atoms? Quantum field theory tells us that what we perceive as a vacuum is a riot of activity, a soup of virtual particles popping into and out of existence. This isn't just a theory. It has measurable effects, like the Casimir effect, where two uncharged plates in a vacuum are pushed together because there are more virtual particles pushing from the outside than from the inside. The void itself is in motion. So, the solid chair is made of atoms vibrating trillions of times a second. Even at absolute zero, they're forced to jitter by quantum mechanics. The electrons within them are blurry clouds of probability. And the empty space between them is a seething cauldron of virtual particles. The quiet solidity of our world is just a large-scale average of an underlying reality that is nothing but chaotic, unending motion. But this is only half the story. Now, we have to stop zooming in and start zooming out. We've journeyed deep into matter and found only motion. Now, let's pull back. Back to you, sitting on a planet that feels as solid as anything can be. You don't feel like you're moving, because everything in your immediate vicinity is moving with you. But the moment we look to the heavens, this illusion shatters. The Earth is rotating on its axis, and your speed can be over 1,000 miles per hour, 1,670 kilometers per hour. That's the first layer. The Earth is also hurtling through space in its orbit around the Sun at about 67,000 miles per hour, 30 kilometers per second. That's the second layer. But our entire solar system is also orbiting the center of the Milky Way galaxy at a speed of about 500,000 miles per hour, 220 kilometers per second. It takes about 230 million years to complete one orbit. The last time we were in this part of the galaxy, dinosaurs were just beginning to appear. That's the third layer. And the Milky Way itself isn't still. It's part of a collection called the Local Group, and our galaxy and its neighbor, Andromeda, are hurtling towards each other at about 250,000 miles per hour, 110 kilometers per second. But what is everything moving relative to? If all the galaxies are moving, what can we use as a fixed reference point? This question brings us to one of the most profound ideas in science, Einstein's theory of relativity. Einstein realized there is no absolute at rest. All motion is relative. If you're on a perfectly smooth train with the windows blacked out, you can't prove you're moving. The laws of physics work the same. You can only say you are moving relative to something else, like the train station. The question, what is our absolute speed, is meaningless. But astronomers did find something that can serve as a universal frame of reference: the cosmic microwave background, or CMB. This is the faint afterglow of the Big Bang, radiation that permeates the entire universe. By measuring tiny temperature shifts in this ancient light, scientists can calculate our motion relative to the CMB itself. When they do, they find that our entire cosmic neighborhood, the Local Group, is streaking through the universe at a combined speed of approximately 1.3 million miles per hour, about 600 kilometers per second. So right now, as you sit there feeling perfectly still, you are on a journey. Your spinning planet is orbiting a star, which is circling a galactic core, which is hurtling through space. Your combined velocity, relative to the echo of creation itself, is over 1 million miles per hour. Stillness is not a state of being, it's a point of view. We began this journey by challenging the apparent stillness of the world. We started with our own minds, discovering that perfect calm is an elaborate illusion, actively constructed by our brains. Then, we dove inward to the scale of atoms and found a world forbidden from ever being still, where quantum mechanics enforces a permanent, jittery motion. Finally, we zoomed out to the cosmic scale and saw that our planet, our star, and our galaxy are all caught in an intricate and unending dance, hurtling through the universe. We learned from Einstein that stillness is not a fundamental state, but a relative perspective. So what does this all mean? We're back where we started, but we see with new eyes. That chair is not just a chair. It is a symphony of motion. It's a storm of probability clouds undertaking an epic voyage across the cosmos. It is a paradox, an object that is both perfectly still from one point of view, and in a state of unimaginable motion from another. The illusion of stillness is perhaps the most necessary one we live with. But by decoding it, we gain a deeper perspective. Reality is not a static collection of things, but a dynamic, interconnected process. The universe is not a noun, it's a verb. And we are not separate observers of this cosmic dance. We are an integral part of it. The fact that you can experience a moment of perceived quiet is not a reflection of the world outside, but a testament to the incredible power of the 3-pound universe inside your skull. This journey reveals that our perception is just one narrow slice of a much grander reality. It reminds us that normal was never the plan. What other illusions do you think we are living with every day? If you've ever felt that disconnect between what feels true and what is true, let us know in the comments. And if you enjoyed this journey into the hidden realities of our universe, consider subscribing. We try to piece together the puzzle of existence here, one strange idea at a time. Thanks for watching. Our world is built on a quiet certainty. The floor beneath our feet, the desk we work at, the cup we hold, they feel firm, dependable, real. They are the anchors of our physical world. But what if that certainty was an illusion? Not a metaphor, but a physical one. An elegant simplification our brains construct, to keep us from seeing the restless, almost impossibly active reality just beneath the surface. That stillness is an invention. That solidity is a fabrication. Because at its most fundamental level, that still rock is a furious swarm of particles, forever shimmering with an energy they can never lose. What we think of as solid is mostly empty space, and what we call still is a microscopic storm of unimaginable speed. This is a journey into the frantic, shimmering, and ultimately empty truth of the world we thought we knew. We learn to trust the solid world from our first moments. We push against the world, and it pushes back. This interaction is so fundamental, we rarely think to ask, why is this table solid? Why doesn't my hand simply pass through it, like a ghost? The common sense answer seems obvious, because it's full of stuff. It's packed tight with matter. But this intuition, as logical as it seems, is where our everyday understanding begins to diverge spectacularly from reality. It's one of the most profound errors in our perception of the universe. If we could shrink ourselves down, past the wood grain, past the cells, down to the atomic level, the world we know would dissolve. The dependable table would be replaced by an astonishing, almost terrifying emptiness. The atoms that make up your desk and your own body are fantastically empty. Imagine an atom is the size of a sports stadium. Its nucleus, where almost all the mass resides, would be a tiny marble suspended in the very center. The electrons, giving the atom its volume, would be like a few grains of sand moving through the vastness of the upper decks. The rest is nothing, a vast emptiness. Your body is made of these empty stadiums. The chair you're sitting on is made of these empty stadiums. So the question becomes urgent. If everything is more than 99.999% empty space, why aren't you falling through your chair right now? The answer isn't about being full. It's about forces. What you feel is solid isn't matter bumping against matter. It's the powerful repulsion of invisible energy fields. As your hand approaches the table, the electron clouds of the atoms in your skin get near the electron clouds of the atoms in the table. Because all electrons have a negative charge, they fiercely repel each other. The sensation of touch is your brain's interpretation of this colossal electromagnetic contest. You never truly touch the table. You are floating an infinitesimal distance above it, held aloft by a force field. But this is only part of the story. The true reason the universe holds its shape is rooted in a law of quantum mechanics so fundamental it dictates the structure of reality. It's called the Pauli exclusion principle, formulated by the physicist Wolfgang Pauli. In essence, it says that no two identical particles, in this case, electrons, can occupy the exact same quantum state in the same place. Think of quantum states as assigned seats in a theater. Each electron has a specific ticket. The Pauli exclusion principle is the non-negotiable rule. No two electrons can hold the same ticket for the same seat. They are fundamentally antisocial particles. When you press your hand on the table, the electrons in your atoms try to move into the space occupied by the electrons in the table. But those seats are taken. The exclusion principle forbids it. To force the issue would require an enormous amount of energy, so much that it's easier to break the table, or the bones in your hand, than to violate this quantum rule. This is the true nature of solidity. It is not a property of matter being full. It is a consequence of quantum law. The world feels solid because of a cosmic game of musical chairs where there are no empty seats. Every mountain, every building, every grain of sand holds its shape because its electrons are stacked in unique, non-negotiable energy levels. Without this principle, all matter would collapse on itself. Solidity isn't a feature of matter. It is a feature of law. Once we look past the illusion of solidity, we find another, the illusion of stillness. The quiet, unmoving object is a myth. The truth is far more dynamic. Let's return to that rock on the table. To our eyes, it's the definition of inert. But if we could hear the atomic world, the silence would be shattered by a deafening roar. Every atom in that rock is in a state of constant, chaotic vibration. The source of this motion is thermal energy. What we perceive as temperature is, at the microscopic level, the raw kinetic energy of atoms. The warmer an object is, the more violently its atoms shake. The speeds involved are staggering. At room temperature, the atoms in a supposedly still object are vibrating at speeds of hundreds of meters per second, in some cases, rivaling the speed of a bullet. Think of that. Every one of the trillions of atoms that make up that simple rock is slamming back and forth in its position at incredible speeds. These atoms are held in a structure called a crystal lattice, a three-dimensional scaffolding. The bonds connecting them act like incredibly stiff springs. Each atom oscillates wildly in its small pocket of space, pulling and pushing on its neighbors and transmitting these vibrations throughout the structure at a frequency of trillions of times per second. So, why don't we feel this? It's a matter of scale and balance. While individual atoms move at incredible speeds, their movements are random and in all directions. For every atom vibrating to the left, another is vibrating to the right. On average, all this frantic motion cancels itself out. The object as a whole goes nowhere. It's like a perfectly balanced contest with trillions of participants, where the immense strain of the effort results in a standstill. The same is true for the wooden desk you might be sitting at. Its molecules are quivering. A diamond, the hardest natural substance, is a paradox of stillness and inner chaos. Its carbon atoms are locked in a rigid structure, yet each one vibrates trillions of times per second. This ceaseless vibration is fundamental. It's how heat is transferred through solids, as these vibrations are passed from one atom to the next. In a very real sense, the sound of this atomic swarm is what we call heat. And so, the quiet object on the table is revealed to be a collective of trillions of individuals, each one rattling the bars of its cell at supersonic speeds. The rock is not a thing, it is an event. A swarm whose inner motion is so perfectly balanced it creates the illusion of peace. We began with a solid object and found an empty structure. We looked at a still object and found a vibrating swarm. Now, we must take the final step, into the quantum realm itself. Because even this picture, of tiny balls shaking, is just another simplification. The reality is far stranger. The particles themselves, electrons, quarks, are not tiny, solid balls. This is a classical idea that dissolves at the quantum scale. Instead, a particle is something far more strange. It is both a particle and a wave. This is the principle of wave-particle duality, a cornerstone of quantum mechanics. What does it mean for a particle to be a wave? It means an electron doesn't have a definite location until it is measured. Instead, it exists as a wave of probability, a ghostly field of potential. Where the wave's amplitude is high, there's a high probability of finding the particle. In a very real sense, the electron is everywhere and nowhere at once, a shimmering cloud of possibility. This wave-like nature demolishes our vibrating balls model. The electrons in an atom aren't little planets, they are standing waves of probability. The atom isn't a tiny solar system, it's a resonant chamber for these ghostly waves. Our picture of the swarm now becomes even more ethereal. It's not a swarm of tiny, definite things. It's a swarm of probabilities, a lattice of shimmering, uncertain clouds. The universe, at its base, is not made of things. It's made of possibilities. This inherent fuzziness is a fundamental feature of reality, codified in the Heisenberg uncertainty principle. It states there is a trade-off in what we can know. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. You can never know both perfectly. And here we find the deepest secret of the swarm. A particle can never be perfectly still. To be perfectly still would mean its momentum is exactly zero, with zero uncertainty. The uncertainty principle forbids this, as it would require the particle's position to be completely uncertain, spread out across the entire universe. Because a particle in an atom is confined to a small area, its momentum can never be exactly zero. This leads to one of the most remarkable concepts in all of physics, zero-point energy. Because of the uncertainty principle, every particle must always possess a minimum, non-zero amount of energy. It's an energy that exists even in the complete absence of heat. If you could cool that rock to absolute zero, minus 273.15 degrees Celsius, where all classical thermal motion is supposed to cease, its atoms would still vibrate, shuddering with this ghostly, inescapable quantum energy. It is the cost of existence. This is the ultimate truth of the swarm. The motion is not just thermal. It is quantum. It is fundamental. The atoms in that rock are jiggling because the laws of the universe forbid them from being still. The swarm is not just active, it is haunted, animated by a restlessness woven into the fabric of spacetime itself. The stillness you see is the most profound illusion of all, hiding a universe that, at its foundation, refuses to sleep. We began with a simple, solid rock, an object of mundane certainty. And at every step, that certainty has dissolved. The solid rock became 99.99% empty space. The still rock became a swarm vibrating at incredible speeds. And finally, that swarm became a ghostly haze, animated by a quantum jiggle it can never escape. The world is not what it seems. Our senses have given us a kind of user interface for reality, designed for survival, not for truth. It edits out the astonishing emptiness, the chaotic motion, and the ghostly uncertainty. It tells us a story of solidity and stillness because that is the story we need to build a shelter and trust the ground we walk on. Our brains are not windows onto reality, they are reality rendering engines. On one hand, this can feel unsettling. The dependable world is a statistical average of an underlying chaos. But on the other, it's a source of profound wonder. It connects us to the universe in the most intimate way. The Pauli exclusion principle, which gives your desk its solidity, is what allows for the rich diversity of chemistry that makes life possible. If electrons were not so antisocial, there would be no atoms as we know them, no molecules, no life. And the idea of zero-point energy is perhaps the most awe-inspiring. It means the universe has a baseline of activity. There is no true, absolute stillness. Even in the coldest void of space, there is a floor of energy, a seething quantum foam. The universe is fundamentally, irreducibly alive with energy. This has real, measurable consequences. The zero-point energy of liquid helium, for instance, is so great it prevents it from freezing under normal pressure, even at absolute zero. In cosmology, the energy of the vacuum is thought to be the driving force behind the accelerating expansion of the universe, what we call dark energy. Living in this restless reality means understanding that stability is an emergent property, not a fundamental one. Order arises from chaos. Stillness arises from balanced motion. Solidity arises from emptiness and law. The universe is not a collection of static objects, but a dynamic network of processes and events. The next time you rest your hand on a table, or simply sit still in your chair, take a moment. Try to imagine what you are not seeing. The vast emptiness within the atoms, bridged by the unyielding force of quantum law. The trillions of atomic nuclei, vibrating with a thermal fury. And beneath it all, the ever-present hum of zero-point energy, the quantum uncertainty that forbids true rest. You are not touching a solid object. You are interacting with a localized storm of probability and energy, held in a delicate and beautiful truce. The solid world is an illusion our minds create to navigate our lives. But the truth, that at its core, that still rock is a furious swarm of particles, forever buzzing with a ghostly quantum energy they can never lose, is infinitely more fascinating. We have journeyed from the familiar to the utterly strange. We started with a simple, solid world, and ended in a universe of shimmering probability and perpetual motion. Beneath the tranquil surface of everything, there is a hidden reality of vast emptiness, of violent atomic vibrations, and of an inescapable quantum jitter that animates the very fabric of space. Every object, no matter how inert it may seem, is a storm of activity, held in a rigid dance by invisible forces and immutable quantum laws. These particles are not solid balls, but ghostly waves of potential, and they are never, ever at rest. The universe is not a quiet place. It is a symphony of vibration. The world is not made of things. It is made of motion. If this journey into the reality beneath our feet has sparked your curiosity and made you question the world around you, perhaps you'll join us for the next one as we continue to peel back the layers of the mundane to reveal the extraordinary truths hidden within. Until then, remember, the next time you sit perfectly still, listen closely. You might just feel the hum of the universe. Imagine the coldest temperature possible. A point so cold that all the heat in the universe has been drained away. A state called absolute zero where, logically, all motion should come to a final, total stop. Picture an atom, frozen in time and space, perfectly still. And that feels right, doesn't it? The final, silent endpoint of cold. But what if I told you that this perfect stillness is a cosmic impossibility? That even at the absolute zero of existence, at -273.15 degrees Celsius, every single atom in your body would still be vibrating with an unstoppable, ghostly energy. What if this vibration isn't a flaw in our cooling methods, but a fundamental law of the universe, powered by the bizarre and frantic energy of pure nothingness? This is the reality of our quantum world. And we're going on a journey to the very bottom of temperature to uncover the profound and deeply strange law that forbids stillness. We'll discover why nothing, not you, not me, not the fabric of space itself, is ever truly at rest. Before we shatter this idea, we have to build it up. And to do that, we need to understand what temperature actually is. We use words like hot and cold every day. But what are we really describing? At its most basic, temperature is just a measure of motion. Specifically, it's the average kinetic energy of the atoms and molecules in a thing. Think of a steaming cup of coffee. On our scale, it's just a hot liquid. But if you could zoom in 1,000,000,000 times, you'd see a chaotic, frenetic dance. Water molecules are zipping around, smashing into each other, vibrating and rotating wildly. This microscopic violence is what your nerves feel as heat. The faster they move, the higher the temperature. Now, picture an iced tea. Zooming in here reveals a much calmer scene. The molecules are still moving, but it's more like a slow waltz than a mosh pit. They have less kinetic energy, so the tea has a lower temperature. For centuries, this link between heat and motion led scientists down a logical path. If adding heat makes things move faster, then removing heat must make them move slower. This leads to a huge question. Is there a limit? Can you keep removing heat forever, or is there a bottom? A point of ultimate cold? In the 18th century, scientists like Guillaume Montans began to suspect there was a limit. By studying gases, they saw a simple relationship. As a gas gets colder, its pressure drops in a straight, predictable line. If you trace that line down, past any temperature they could actually create in a lab, all the lines for different gases pointed to a single, theoretical spot. A point where the pressure of a perfect gas would drop to zero. This point was a mathematical ghost. A British physicist, William Thomson, later known as Lord Kelvin, realized this was a fundamental limit of nature. It was the point where the energy of motion itself seemed to vanish. He called it absolute zero, the true zero point of temperature, and created a new scale in its honor, the Kelvin scale, which starts at 0 K. This gave physicists a beautiful, elegant picture of reality. Imagine cooling a block of iron. The iron atoms, arranged in a crystal lattice, are jiggling furiously. As you pump the heat out, their jiggling slows. The violent shiver becomes a gentle tremor. The tremor becomes a faint hum. Slower, and slower, and slower. The classical dream was that at 0 Kelvin, the hum would finally stop. Each iron atom would settle perfectly into its spot, all kinetic energy gone. The universe, in this small region, would achieve perfect order, perfect silence, and perfect, absolute stillness. It's a deeply satisfying idea. And it is completely wrong. The beautiful rules of classical physics, which described everything from planets to billiard balls, all predicted this state of absolute stillness. But at the dawn of the 20th century, a revolution was brewing. Scientists studying the world of the very small, atoms and electrons, found that the old rules just didn't work. The universe, at its most fundamental level, played by a different, much weirder set of rules. These new rules were called quantum mechanics. And one of the first and most profound casualties of this new physics was the dream of absolute zero. So, let's go back to our atom, cooled to 0 Kelvin. Classical physics says it should be perfectly still. But quantum mechanics screams, no. It says this state of perfect rest is forbidden. It's not just hard to achieve, it violates the most fundamental laws of reality. Even at their lowest possible energy state, particles are condemned to a life of constant, inescapable motion. This is the twist in our story. The serene, motionless crystal is a fantasy. The reality is that even at the coldest temperature possible, that block of iron would be a mass of shivering activity. Every atom would be fidgeting in its place with a tiny, relentless energy. This isn't leftover heat, we've removed all of that. This is something else entirely. A new kind of energy, born from the quantum world itself. This immediately presents a riddle. Why? Why would the universe care if a particle stops moving? What's so special about motion that it can never be allowed to end? To a classical physicist, this would sound absurd. A particle is a particle. It has a position and it has a speed. If its speed is zero, it's at rest. Simple. But in the quantum world, things are never that simple. To be perfectly still, to have a momentum of exactly zero while also having a defined location, would be to know two things about that particle with absolute certainty. And it's here, in this demand for certainty, that we find the crack in the classical foundation. Because the universe, at its core, is built on a bedrock of uncertainty. To understand why nothing can ever be still, we have to meet the man who first wrote down this cosmic law of fuzziness, and grapple with his most famous, and most misunderstood, principle. In the 1920s, physics was in glorious chaos. The old world was crumbling, and a new, bizarre quantum reality was taking its place. At the heart of this revolution was a young German physicist named Werner Heisenberg. In 1927, Heisenberg unveiled the concept that would seal the fate of absolute stillness forever: the Heisenberg uncertainty principle. Now, you've probably heard a version of this principle explained as the observer effect. The idea is that the act of measuring something tiny, like an electron, inevitably disturbs it. But while the observer effect is real, it's not the deep meaning of the uncertainty principle. The principle isn't about our clumsy tools, it's about a fundamental limit of reality itself. The uncertainty principle states that there are pairs of properties of a particle, like position and momentum, that are locked in a cosmic trade-off. Momentum is just mass times velocity, so you can think of it as a measure of motion. Heisenberg's principle says you can't know both the precise position and the precise momentum of a particle at the same time. The more you pin down one, the fuzzier the other becomes. It's not that the particle has a definite position and momentum that we are just too clumsy to measure. It's that the particle simply does not possess both properties with perfect sharpness at the same time. Reality itself is fuzzy. Let's use a better analogy. Forget tiny billiard balls and think about waves on a pond. Imagine a long, rolling wave. You can easily measure its wavelength, which is like a particle's momentum. But if I ask you, where, exactly, is the wave? The question doesn't make much sense. The wave is spread out. It has a well-defined momentum, but a very uncertain position. Now, imagine creating a single, sharp splash. If I ask where the wave is, the answer is easy: it's right there. Its position is well defined. But what is its wavelength? The concept is meaningless for a single spike. It's a jumble of many different wavelengths all added together. So, it has a well-defined position, but a very uncertain momentum. Quantum particles are like this. They have an inherent wave-particle duality. So, what does this have to do with our atom at absolute zero? Well, if our atom became perfectly still, its momentum would be exactly zero. We would know its momentum with 100% certainty. According to the uncertainty principle, if you know the momentum perfectly, the uncertainty in its position must become infinite. This means the atom could be literally anywhere in the universe. But that's a paradox. Our atom is trapped in a crystal, or in a lab. It has a location, even if it's a bit fuzzy. The universe is faced with a contradiction. To solve it, it strikes a compromise. The particle is forbidden from ever reaching exactly zero momentum. It must always keep a tiny, residual amount of motion, a fundamental, inescapable, jiggle. This jiggle ensures its momentum is never perfectly zero, which allows its position to be localized enough for it to exist in a specific place. The particle sacrifices perfect stillness to satisfy the universe's demand for uncertainty. This minimum, non-zero energy of motion is the solution to our riddle. It's the reason you are still vibrating, and it has a name: zero-point energy. So, particles can never be still, thanks to the uncertainty principle. They are forever doomed to a perpetual jiggle called zero-point energy, ZPE. But where does this energy come from? If we've removed all the heat, what's powering this motion? The answer is one of the most mind-bending concepts in physics. The energy comes from the vacuum of space itself. In our classical view, a vacuum is the definition of nothing. But the quantum vacuum is anything but empty. According to quantum field theory, the universe is made of continuous, fluctuating fields. A particle is just a ripple in its corresponding field. The quantum vacuum is the lowest energy state of all these fields, but lowest doesn't mean zero. Thanks to uncertainty, these fields can never be perfectly flat and still. They are a seething, bubbling, frantic cauldron of virtual particles, popping in and out of existence. This is the source of zero-point energy. Our atom, sitting in what we thought was an empty void, is actually immersed in this turbulent quantum sea. It's constantly being nudged and buffeted by these virtual particle fluctuations. This all sounds like wild speculation, but ZPE has real, measurable effects. The most famous proof is the Casimir effect. In 1948, physicist Hendrik Casimir made a strange prediction. Imagine two perfectly flat, uncharged metal plates in a vacuum, placed incredibly close together. He realized that because the space between the plates is so small, it restricts which virtual particles can pop into existence there. There are more virtual particles in the open space outside the plates, pushing in, than there are between the plates, pushing out. This creates a tiny, measurable force that pushes the plates together. This force was experimentally measured in 1997 by Steve Lamoureux, and the results matched the predictions. The energy of pure nothingness was physically pushing two objects together. We also see its effect in the element helium. Every element except helium will freeze solid if you get it cold enough. But at normal atmospheric pressure, you can cool helium all the way to absolute zero, and it will remain a liquid. Why? Its atoms are very light and the forces between them are weak. The zero-point energy, that inescapable quantum jiggle, is so strong for helium atoms that it overcomes the forces that would normally lock them into a solid. The atoms literally jiggle too much to freeze. You have to apply over 25 atmospheres of pressure to finally force helium to solidify. Zero-point energy isn't a fringe idea. Its fingerprints are all over the physical world. But the story gets even stranger, because we have now seen it move objects on a human scale. It's easy to think of this as just a microscopic curiosity. But what if this quantum jiggle could affect things we can actually see? The definitive proof came from one of the most sensitive scientific instruments ever built, LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO's job is to detect faint ripples in spacetime called gravitational waves. To do this, LIGO has to be almost perfectly still. It uses lasers bounced between mirrors to measure distances smaller than a proton's width. Scientists shielded the instrument from every vibration imaginable and cooled its core components. But even after eliminating all classical noise, they hit a wall. Their mirrors were still moving. These weren't small mirrors. They were test masses of fused silica, each weighing 40 kilograms, about 88 pounds. And these human-sized objects were being measurably jiggled. The culprit wasn't a flaw. It was quantum mechanics. A landmark 2020 paper reported the direct measurement of quantum effects on these 40-kilogram mirrors. It wasn't the vacuum alone kicking them, but something even more subtle: the quantum nature of the laser light used for the measurement itself. The laser is made of photons, and the uncertainty principle creates a trade-off. To get a very precise measurement of the mirror's position, you need a lot of photons, but the random arrival of these photons creates a fluctuating radiation pressure that kicks the mirror, making its momentum uncertain. This quantum noise caused the 88-pound mirrors to move back and forth by about 10 to the power of minus 20 meters, a distance a billion times smaller than a single atom. As lead scientist Nurgis Mavalvala put it, we too, every nanosecond of our existence, are being kicked around, buffeted by these quantum fluctuations. To prove they were seeing a quantum effect, the scientists used a quantum squeezer. This device manipulates the uncertainty of the laser light itself. They could squeeze the uncertainty in one property, which, as the principle demands, increased the uncertainty in the other, making the mirrors jiggle more. By controlling this trade-off, they proved they were witnessing a Heisenberg limited interaction between light and a macroscopic object. This demolishes the clean line between the quantum and classical worlds. We've established that the universe forbids true stillness, enforcing a perpetual jiggle on everything. For centuries, perpetual motion was seen as impossible. But what if a system could take this fundamental quantum jiggle and turn it into an organized, eternal dance? This question leads us to one of the most exotic phases of matter ever conceived, the time crystal. First proposed in 2012 by Nobel laureate Frank Wilczek, a time crystal does something truly bizarre. A normal crystal, like a diamond, has a structure that repeats in asterisk space. A time crystal has a structure that repeats in asterisk time. Even in its lowest possible energy state, its ground state, equivalent to being at absolute zero, the particles inside a time crystal are in constant, repetitive motion. They oscillate in a never-ending cycle, without any energy input. Think of a pendulum that swings forever without slowing down. Classically, that's impossible. But a time crystal is a quantum system at its minimum possible energy. It has no energy left to lose. It can't come to rest, because its state of rest is a state of perpetual motion. Scientists have now created these strange objects in labs. Time crystals are the ultimate expression of the universe's restless nature. They prove that in the quantum world, the most stable state isn't always stillness. Sometimes, it's a never-ending dance. Our journey started with a simple idea. Absolute cold means absolute stillness. We pictured a world drained of all energy, where the dance of atoms finally ceases. But as we descended into the quantum realm, we found this serene picture was a mirage. The universe is governed by the Heisenberg uncertainty principle, which declares perfect stillness impossible. This cosmic rule enforces a perpetual vibration on every particle, known as zero-point energy. We discovered this energy comes from the quantum vacuum itself, a seething foam of virtual particles that nudges everything in the cosmos. We saw its proof in the real world. In the liquid state of helium at absolute zero, in the force pulling two mirrors together in a vacuum, and in the quantum jiggles of 40-kilogram mirrors at LIGO. So, the next time you feel perfectly still, remember that you are a symphony of vibration. Every one of the trillions of atoms that make you is locked in an eternal dance, humming with an energy baked into the very structure of reality. The universe is not a quiet, static place. It is a restless, energetic sea, and even at absolute zero, you are, and will always be, vibrating with the unstoppable hum of the cosmos. What other quantum mysteries make you question the nature of reality? Let me know in the comments below. And if you enjoyed this journey into the bizarre heart of physics, make sure to subscribe and hit the bell so you don't miss our next exploration. What is nothing? Take a moment. Really think about it. If you created the most perfect, absolute emptiness possible, what would be left? Our intuition tells us that if you take a box and remove everything, every atom, every speck of dust, every last particle, what's left is, well, nothing. An empty stage. A silent, static void. For most of history, this was the answer. An absence. A nullity. The definition of zero. According to everything we thought we knew, a perfect vacuum should be the most boring place in the universe. A place where, by definition, nothing can happen. So, what happens if you place two perfectly smooth, uncharged mirrors in a perfect vacuum, totally isolated from everything? According to the classical laws of physics, the rules that govern our everyday reality, the answer is simple: absolutely nothing. The mirrors should just hang there, motionless, forever. But that's not what happened. In a real experiment, scientists discovered something that defies all our gut feelings. The mirrors started to move. Slowly, but undeniably, something began pushing them together. There was no wind, no vibration, no electricity. The force came from the nothingness itself. This is the story of how we discovered that empty space isn't empty at all. In fact, it's a roiling, chaotic, and unimaginably energetic place. This is the story of the Casimir effect, physical proof that the vacuum itself contains a hidden energy that changes everything we thought we knew about our universe. And it all started with a simple question: what happens when you look at nothing? To get why two moving mirrors is such a big deal, we need to appreciate the idea it shattered. The concept of nothing has been a battleground for thinkers for millennia. The ancient Greeks were split. Philosophers like Parmenides argued that a true void was a logical impossibility. What is, he'd say, and what is not, can't be. To talk about a place where nothing exists was nonsense. Aristotle took this further with his famous declaration, "Nature abhors a vacuum." He believed space was a asterisk plenum, a substance, and any void would be instantly filled by matter rushing in. For nearly 2,000 years, this idea held. The universe was seen as full, with no room for pure nothingness. Then the scientific revolution started poking holes in this. In the 17th century, Evangelista Torricelli created the first man-made vacuum with his mercury barometer experiments. He showed that a column of mercury in a tube would leave an empty space at the top, the Torricellian vacuum. It was a pocket of nothing, right here on Earth, and a direct challenge to Aristotle. This set the stage for Isaac Newton. His universe was a vast, cold, and mostly empty stage. He proposed an absolute space, an invisible and unchanging 3D grid. This space was the passive backdrop for all motion. It was empty, and it did nothing. For Newton, the void didn't play an active role, it was just there. Or rather, not there. This view dominated for centuries, but it had problems. A big one was light. How did light travel from the sun to the Earth across a supposedly empty void? In the 19th century, physicists proposed the luminiferous ether, an invisible, massless fluid that filled all of space and carried light waves. It was a last, desperate attempt to fill the void. But every experiment to detect this ether, most famously the Michelson-Morley experiment in 1887, failed. The nail in the ether's coffin came in 1905 with Albert Einstein's theory of special relativity. Einstein's big idea was that the speed of light in a vacuum is a universal constant. This elegant concept made the ether completely unnecessary. Light didn't need a medium, it could travel through a true, perfect vacuum. So, by the early 20th century, science was back to a vision of an empty void. The vacuum was the baseline of reality. It had no properties, no substance, no energy. It was the definition of zero. And it was into this perfectly silent and boring void that a new theory was about to be born. A theory that would find the void wasn't silent but screaming with energy. Our story jumps to the years after World War II. At the Philips Research Labs in the Netherlands, a brilliant Dutch physicist named Hendrik Casimir was wrestling with a seemingly unrelated problem: sticky liquids. He was studying colloidal solutions, like milk or paint, trying to understand the van der Waals forces, the weak attractions between neutral molecules that, for instance, let a gecko stick to a ceiling. Casimir was trying to figure out why these solutions were sometimes unstable. He and his collaborator, Dirk Polder, developed a theory, but Casimir found the math ugly and complex. As the story goes, he vented his frustrations to the legendary Niels Bohr, one of the fathers of quantum mechanics. Bohr muttered something like, "It must have something to do with zero-point energy." That offhand comment sent Casimir down a rabbit hole that would change physics. He dropped the messy liquids and focused on a much cleaner scenario, one that would isolate the vacuum itself. He imagined two perfect, uncharged metal plates, parallel to each other in a total vacuum. Let's be clear about this setup. The plates are perfect mirrors. They have no electric charge, so no static cling. The whole thing is in a vacuum chamber with all the air pumped out. And it's all cooled to absolute zero, or as close as we can get. This is key. Cooling it removes all heat. Every known, classical source of force has been eliminated. According to classical physics, nothing should happen. The plates are neutral. There's no air. There's no heat. They should stay perfectly still forever. But Casimir, guided by Bohr's cryptic hint, realized that the new rules of quantum mechanics predicted something else. In 1948, he He published a paper with an astonishing prediction. Even in this perfect vacuum, a force would arise from the nothingness and push the plates together. He had found a force in nothing. For years, this was just a theoretical curiosity. The predicted force was so mind-bogglingly small that measuring it was impossible at the time. At a separation of 1 micrometer, the width of a bacterium, the force is minuscule. Only when you get them to about 10 nanometers apart, roughly 100 atoms wide, does the pressure become substantial. But getting two surfaces that close without them touching, while keeping them perfectly parallel, is an immense challenge. Early attempts, like one by Marcus Sparni in 1958, couldn't confirm it. The errors were just too big. For nearly 50 years, the Casimir force existed more on paper than in the lab. The definitive proof had to wait until 1997. At Los Alamos National Laboratory, physicist Steve Lamoureux finally did it. He used a clever setup with a torsion pendulum and, instead of 2 flat plates, he used 1 flat plate and 1 spherical one. This made the distance much easier to control. The results were unmistakable. A force was measured, and its strength matched Casimir's 1948 prediction to within 5%. After half a century, the impossible was confirmed. 2 uncharged mirrors, in an empty, freezing vacuum, really did push each other together. Hendrik Casimir, who passed away in 2000, lived to see his extraordinary prediction vindicated a few years earlier. The question was no longer if the force existed, but why. The answer would tear up our definition of nothing. So, where does this force come from? If there's nothing between the plates, what's pushing? The answer lies in one of the most powerful and weirdest theories ever devised: quantum field theory, or QFT. QFT paints a radical new picture of reality. Forget tiny, solid particles. According to QFT, the most fundamental things in the universe are not particles. They're fields. Imagine the entire universe is filled with invisible, fluid-like substances. These are the fields. There's one for each fundamental particle: an electron field, a quark field, and, for our story, an electromagnetic field. These fields are everywhere. So what are particles? In this view, particles are just ripples or vibrations in their fields. Think of a vast, calm ocean. The ocean is the field. If you tap the surface, you create a ripple. That ripple is the particle. An electron is a ripple in the electron field. A photon of light is a ripple in the electromagnetic field. The universe isn't tiny billiard balls moving through an empty void. The universe is a collection of these vast, interconnected fields. The fields are the reality. Particles are just their temporary, energetic whispers. This brings us back to the vacuum. What is a vacuum in QFT? Classically, it's a space with all particles removed. But in QFT, that's not enough. Removing the particles is just like calming the ocean so there are no more ripples. But even when the ripples are gone, the ocean is still there. A quantum vacuum is when you've removed all the particles, the ripples, but the fields themselves remain. And here's where it gets weird. You'd think the fields would be perfectly still, holding a value of exactly 0. But they can't be. The reason is a cornerstone of quantum mechanics: the Heisenberg uncertainty principle. First proposed by Werner Heisenberg in 1927, the uncertainty principle is a fundamental law of nature. It states that you can never know certain pairs of properties simultaneously with perfect accuracy. The more you know a particle's position, the less you know its momentum, and vice versa. But another version of this principle relates energy and time. It means you can't know the exact energy of a system over a very short time. Reality has a built-in fuzziness. Now, apply this to a quantum field in a vacuum. If the field were perfectly still with 0 energy, we'd know its state with absolute certainty. Its energy would be 0, and its rate of change would be 0. That would violate the uncertainty principle. A quantum system can never be perfectly at rest. Think of a guitar string. Even when it's as quiet as it can be, it has a tiny, residual vibration, its zero-point mode. A quantum field is the same. It must always be jittering, always fluctuating, even in a total vacuum at absolute zero. This constant, unavoidable jittering is what we call vacuum fluctuations or zero-point energy. The vacuum, the supposed nothingness, is actually a seething cauldron of activity. The empty space around us is boiling with the energy of these fields. The void is not void, it's alive. This zero-point energy isn't just math. It has real consequences, the strangest of which is the concept of virtual particles. Because a field's energy can fluctuate for short moments, it can effectively borrow energy from the vacuum. If it borrows enough, it can create a particle-antiparticle pair, a ripple and an anti-ripple. For example, the electromagnetic field can spontaneously create an electron and its antimatter twin, a positron. These particles are virtual because they don't stick around. They pop into existence from nothing, live for an impossibly brief moment, and then annihilate each other, returning the energy before the universe notices any violation of energy conservation. It's like a form of quantum embezzlement. As long as you pay it back fast enough, you get away with it. So the vacuum isn't just fluctuating fields. It's a chaotic sea of virtual particles, constantly winking in and out of existence, everywhere, at every moment. Space isn't a tranquil void but a frantic, subatomic foam. The physicist John Wheeler, who coined the term quantum foam, said if you could zoom in to the tiniest possible scale, spacetime would look like a turbulent, bubbling ocean. You might be thinking, if these particles are virtual, how do we know they're real? It's a fair question. While we can't see them directly, we see their effects. They subtly influence the real particles we can see. One of the first clues was the Lamb shift. In the 1940s, Willis Lamb discovered a tiny, unexpected shift in the energy levels of the hydrogen atom. Theory said two specific levels should have identical energy, but his measurements showed they were slightly different. The reason? The sea of virtual particles in the vacuum was gently nudging the atom's electron, changing its energy just enough to match what Lamb saw. The virtual particles were leaving fingerprints on the real world. And this brings us back, finally, to our two mirrors. Hendrik Casimir's great insight was realizing that these virtual particles, specifically, virtual photons, were the key. He understood that the presence of the mirrors would alter the very fabric of the vacuum. We now have all the pieces. Two perfect mirrors in a vacuum. And we know this vacuum is actually a roiling sea of virtual photons of all possible wavelengths, popping in and out of existence. Now, think about the space outside the two mirrors. Here, virtual photons of every conceivable wavelength can exist. Long wavelengths, short wavelengths, everything in between. The vacuum outside is a complete spectrum of quantum chaos. But what about the space between the two mirrors? This is the crucial part. The mirrors act like the ends of a guitar string. A guitar string, fixed at both ends, can only vibrate at specific frequencies, a fundamental note and its overtones. Similarly, the virtual photons between the plates are constrained. Their wavelengths have to fit neatly between the plates a whole number of times. This means the space between the mirrors acts as a filter. It excludes all the virtual photons whose wavelengths are too long to fit. The vacuum between the plates is still active, but it's a * lesser activity. Many of the long wavelength fluctuations are suppressed. So you end up with a pressure imbalance. The vacuum outside the plates has a full spectrum of virtual photons pushing on the mirrors. The vacuum inside the plates is a more subdued version, with fewer long wavelength fluctuations. The result is that there are more virtual photons bouncing off the outside of the plates than there are on the inside. This creates a net force pushing the plates inward. That's the Casimir force. It's a pressure difference that comes from the structure of the quantum vacuum. The force isn't from the plates themselves. It's from the empty space around them. The nothingness is pushing. A great analogy is two ships on a choppy ocean. Out on the open sea, big, long waves hit the outer hulls. But in the narrow channel between the ships, those long swells can't form. Only smaller, choppier waves exist there. The pressure from the big waves on the outside pushes the ships together. The mirrors are the ships, and the virtual photons are the ocean waves. This also explains why the force depends so strongly on distance. When the plates are far apart, they barely affect the vacuum. The space inside is almost identical to the space outside, and the force is negligible. But as you bring them closer, you exclude more and more wavelengths. You filter out more of the vacuum's energy. The pressure difference grows dramatically. Casimir's math showed the force increases with the inverse fourth power of the distance. Halve the distance, and the force gets 16 times stronger. This is why the effect is only measurable at tiny, sub-micron separations. Confirming the Casimir effect was more than just a quirky victory for theory. It was a profound statement about reality. It proved, tangibly, that the vacuum is not a void. It's a physical thing with real energy. This isn't philosophy, it's an experimental fact. You can put two pieces of metal in nothing and watch that nothing push them together. This has huge consequences. In the world of nanotechnology and microscopic machines, MEMS, the Casimir effect is a major engineering challenge. When you're building tiny gears and levers only nanometers apart, this force from nothing can become the dominant force, causing parts to stick together and fail. Nano-engineers have to design around the energy of the void. But the implications go much deeper, to the edge of the cosmos itself. One of the biggest mysteries in cosmology is the accelerated expansion of the universe. In the late 1990s, astronomers discovered that the universe's expansion is speeding up. To explain this, they proposed dark energy, a mysterious, repulsive energy built into the fabric of spacetime. When physicists realized the vacuum has its own energy, the zero-point energy shown by the Casimir effect, they had a tantalizing thought. Maybe vacuum energy is dark energy. It seemed like a perfect match. So, they calculated the total energy density of the quantum vacuum. And the result was a catastrophe. The theoretical value for the vacuum's energy was stupendously, absurdly, mind-bogglingly enormous. Depending on how you calculate it, the predicted value was somewhere between 60 and 120 orders of magnitude larger than what we observe as dark energy. This is, without a doubt, the single worst theoretical prediction in the history of physics. It's a number so wrong it's almost funny. If the vacuum energy were really that large, its gravity would have ripped the universe apart fractions of a second after the Big Bang. We wouldn't be here. This colossal screw-up is known as the cosmological constant problem. It's one of the deepest and most embarrassing puzzles in physics. On one hand, the Casimir effect proves vacuum energy has real mechanical effects. On the other, cosmology shows its gravitational effect is tiny, almost zero. How can both be true? Somehow, an unknown mechanism must be canceling out almost all of this enormous energy, leaving just the tiny bit we see as dark energy. We have no idea what this mechanism is. Some theories speculate about extra dimensions or new symmetries. Others turn to more exotic ideas, like the anthropic principle, that we just happen to live in a universe where the value is, by chance, just right for us to exist. We don't have the answer. The Casimir effect, in solving one mystery, opened the door to a far greater one. It's a signpost at the border of our knowledge, pointing to where our two best theories of the universe, quantum field theory and general relativity, completely failed to agree. The story of two mirrors in a vacuum has taken us on an incredible journey. It forced us to throw out a 2,000-year-old idea of emptiness and replace it with a vision of a dynamic, chaotic reality hiding just beneath the surface. The void is not empty. The ground state of the universe is not zero. Nothing is a fizzing sea of potential, a quantum foam where particles are born from nothing and vanish in an instant. And this isn't speculation. The Casimir effect is the proof. It's the force of the vacuum made real. This discovery changes how we see everything. The silent space between the stars isn't silent. The empty room you're in isn't empty. Every cubic centimeter of the universe, including the space inside you, is humming with this incredible energy. We are swimming in a hidden ocean, revealed only by the gentle push of a force from nothing. It's a discovery that created a puzzle, the cosmological constant problem, that pushes the absolute limits of our understanding. It shows that even now, fundamental parts of our universe remain profoundly mysterious. So the next time you look at the dark emptiness of the night sky, remember what the Casimir effect taught us. It's not nothing. It's a place of immense energy and deep mystery. A place where we found a force in nothing, and found that it changes everything. What part of this quantum reality do you find the most mind-bending? The idea of virtual particles, the energy of empty space, or the colossal mystery of the cosmological constant? Let us know in the comments below. And if you enjoyed this journey to the edge of reality, be sure to subscribe for more explorations into the secrets of our universe. There is a perception, familiar to all of us, of complete stillness. A quiet room, a held breath. It feels like a fundamental state of being, a baseline from which all motion begins. But this is an illusion. Right now, you are on a journey. It is a journey you cannot stop, through a dimension you cannot point to. You are never truly at rest. You are, fundamentally, a traveler through time. If we could freeze the universe, stopping every atom, it might seem peaceful. Physics, however, suggests such a state is impossible. Time itself does not permit it. Over the next few minutes, we will explore why nothing is ever truly still, and what this constant, hidden motion reveals about the structure of reality. The human experience is built around the sensation of rest. In our daily lives, motion is an action we choose to initiate. To stop is to be still. This is our intuitive reality, but it is a reality that does not align with the underlying physics of the cosmos. The universe has a fundamental rule. There is no such thing as absolute rest. Motion is not an activity, it is the constant, inescapable state of everything. The reason for this cosmic restlessness is time. We experience time as a measurement, a way to order events. But in physics, time is a dimension. Just as we have 3 dimensions of space, length, width, and height, time is the fourth, and together they form a single, unified fabric known as spacetime. Before the 20th century, space and time were thought to be separate. Thinkers like Hermann Minkowski demonstrated that they are fused into one 4-dimensional continuum. Your location is not just a point in space, it is an event in spacetime. To fully describe your existence, 4 coordinates are required. 3 for your position in space, and 1 for your position in time. You can choose to stop moving through space, to sit in a chair and remain in the same location relative to the room around you. But you cannot stop moving through time. The clock moves forward. Every second, you are propelled 1 second into the future. You are moving through the time dimension at a constant speed, 1 second per second. This reveals a deep principle. The total motion of any object through the 4 dimensions of spacetime is constant, and this constant is the speed of light. This means motion is allocated between space and time. The more you move through space, the less you move through time. And the less you move through space, the faster you move through time. When you are sitting, perfectly still, you are actually moving through the time dimension at your maximum possible speed. Your entire velocity through spacetime is directed along the time axis. When you begin to walk, a small fraction of that motion is diverted into the dimensions of space. As a result, your movement through time must slow down, a phenomenon known as time dilation. At everyday speeds, this effect is imperceptible, but it is real and has been measured. A clock on a fast-moving jet ticks slightly slower than a clock on the ground. Stillness, then, is not an absence of motion. It is a specific kind of motion, one entirely dedicated to traveling through time. The journey is not optional. As long as time passes, you are in motion. The concept of perpetual motion becomes even more fundamental when we move from the human scale down into the quantum realm. Here, the idea of a particle being still is a physical impossibility, forbidden by the laws of nature. This story begins with the search for absolute zero, the coldest possible temperature, 0 Kelvin, or minus 273.15 degrees Celsius. Classical physics predicted that at this temperature, all thermal motion would stop. Atoms would come to a perfect halt. But the laws of quantum mechanics revealed something different. Even at absolute zero, particles can never stop moving. This residual motion is called zero-point motion, and it arises from the Heisenberg uncertainty principle. Formulated by Werner Heisenberg in 1927, this principle states there is a fundamental limit to how precisely we can know certain pairs of a particle's properties. The most well-known pair is position and momentum. The more precisely you know a particle's location, the less precisely you can know its momentum, and vice versa. This is not a limitation of our instruments, it is a feature of the universe. To say a particle is perfectly still would mean its momentum is exactly zero, with no uncertainty. According to the uncertainty principle, if the uncertainty in momentum were zero, the uncertainty in its position would become infinite. The particle would have to be everywhere in the universe at once. A particle, therefore, can never have a momentum of exactly zero. It must always possess a minimal, unavoidable amount of motion. This minimal energy is called zero-point energy. It is the energy a system has in its lowest energy state, at absolute zero. Molecules continue to vibrate and jiggle, even when they are as cold as they can possibly be. This has observable consequences. Helium, for instance, when cooled to near absolute zero at normal pressures, does not freeze into a solid. It remains a liquid, a superfluid, because the zero-point energy of its atoms is greater than the energy required to lock them into a solid lattice. The atoms jiggle too much to settle into place. The universe, it seems, has a fundamental, low-level hum. Even the vacuum of empty space is not truly empty or still. It is a field of potential, filled with virtual particles emerging and vanishing, driven by this zero-point energy. Relativity showed us that what we call rest is motion through time. Quantum mechanics tells us that even if we could pause that journey, the very components of our bodies would refuse to be still, locked in a perpetual motion dictated by the grammar of reality. We have seen that the passage of time and the laws of quantum mechanics both prohibit true stillness. A third perspective, from Einstein's theory of special relativity, removes the very concept of a universal, rest frame. It shows us that all motion is relative. For Isaac Newton, space was an absolute, unmoving stage. It was a fixed grid against which all motion could be measured. In this view, absolute rest, being stationary against this universal backdrop, was a meaningful concept. But Einstein's revolution was to demolish this idea. He proposed that there is no privileged frame of reference in the universe. There is no universal, still, point. You can only be moving relative to something else. Imagine being on a perfectly smooth train with no windows. If you throw a ball into the air, it goes up and comes straight back down. From your perspective, you and the ball are at rest. But to someone on the platform watching the train pass, you and the ball are moving at 100 kilometers per hour. They see the ball trace an arc. The question of who is really moving is meaningless. Both observers are in valid inertial frames of reference, and the laws of physics are identical for both. You are at rest relative to the train. The observer is at rest relative to the Earth. The Earth moves relative to the Sun. The Sun moves relative to the center of the Milky Way. The Milky Way moves relative to the Andromeda Galaxy. There is no ultimate anchor. There is no absolute rest. This has a profound consequence for our concept of time, known as the relativity of simultaneity. We assume the word now means the same thing for everyone. But whether two separate events happen at the same time is not absolute. It depends on the observer's motion. Consider a long train car with a light in the exact center and a light-activated door at each end. An observer inside the train flashes the light. Since the light travels the same distance to each door, this observer sees them open simultaneously. Now, consider an observer on a platform as the train moves past. From her perspective, the light is emitted, but the train itself moves forward. The rear door moves toward the point of emission, so the light has a shorter distance to travel. The front door moves away, so the light has a longer distance to travel. The platform observer sees the back door open before the front door. Two events that were simultaneous for the observer on the train are not simultaneous for the observer on the platform. Both are correct. There is no universal, absolute, now. This removes the last support for the idea of absolute stillness. Stillness implies a single, shared moment, a universal, now, in which things can be at rest. But if now itself is relative, then rest must also be relative. Your state of stillness in a chair is one perspective. For an astronaut in orbit, you are moving at nearly 28,000 kilometers per hour. For an observer in another galaxy, you are part of a structure spinning and moving through the intergalactic void. There is no place in the universe to be truly at rest. We now turn to a third area of physics: thermodynamics, the science of heat, energy, and entropy. It is entropy that gives us the most profound reason why the universe must remain in a state of perpetual change. This brings us to the arrow of time. We experience time as having a clear direction. We remember the past, and we move into an unknown future. A glass can shatter, but we do not see its pieces spontaneously reassemble. This one-way direction is driven by the second law of thermodynamics. This law states that in an isolated system, the total entropy, a measure of disorder, can only increase or stay the same. It never decreases. A highly ordered state, like a new deck of cards, has low entropy. A shuffled deck has high entropy. There are vastly more ways for a system to be disordered than ordered, so over time, systems naturally evolve towards states of higher entropy. This relentless increase in the universe's total disorder is what gives time its direction. It is the physical process that distinguishes past from future. A state of absolute stillness would be a state of perfect order and zero change in entropy. It would be a system frozen, where no processes occur. The third law of thermodynamics addresses this, stating that it is impossible to reach absolute zero through any finite number of steps. You can get closer and closer, but the destination remains unreachable. Since absolute zero is the theoretical state where all thermal motion would cease, the impossibility of reaching it is another declaration that perfect stillness is impossible. But the arrow of time offers a deeper reason. If time is defined by the process of increasing entropy, by change itself, then a state without change is a state without time. To freeze the universe in a state of absolute rest would be to stop the arrow of time. Without the passage of time, no events could occur. The universe would be a static photograph, devoid of process. The notion of time as a river is an ancient one, but physics gives it a concrete foundation. The flow of time, driven by entropy, forces perpetual change upon the universe. It prevents the cosmos from settling into a final, static state. Motion is not just a property of objects in the universe, it is a fundamental property of the universe itself. We began with the simple sensation of being still. We journeyed to the quantum realm, where particles move with an energy that cannot be extinguished. We moved through the cosmos with relativity, to find that stillness is a matter of perspective. And we saw how the arrow of time is itself an engine of perpetual change. The conclusion is inescapable. At every level of reality, motion is constant. Stillness is the illusion. This reframes our place in the cosmos. The debate between thinkers like Newton, who conceived of an absolute space and time, and Leibniz, who argued that space and time were purely relational, finds a resolution in modern physics. Leibniz was closer to the truth. There is no absolute stage, only the dynamic, interconnected dance of everything in the universe. We are not actors on a stage, we are part of the stage itself. This connects us to everything else. The same laws that guide the orbits of planets are the laws that propel you through the dimension of time. The quantum motion in the atoms of your body is an echo of the energy that fills the vacuum of space. You are not separate from the universe, observing it. You are a part of the universe. From this perspective, our existence is not a state, but a process. Not a thing, but an event unfolding through spacetime. The person you were a moment ago is in your fixed past. The person you will be is in the open future. The only you that exists is the one in this fleeting, ever-moving present. This constant motion is the definition of being. To wish for true stillness would be to wish for non-existence. To stand still is to fall out of time. So the next time you sit, close your eyes, and feel that sense of perfect stillness, remember the truth. Remember the river of time carrying you forward. Remember the energetic dance of the atoms within you. Remember the earth spinning, orbiting the sun, as the sun itself moves through the Milky Way. You are a traveler, a collection of ancient matter, animated by the fundamental laws of the universe, moving through the fourth dimension. You are not at rest. You never have been, you never will be, and in that constant, unstoppable journey is the essence of existence. This channel is a space for these kinds of explorations into science and the nature of reality. A large part of that exploration is the discussion we have together. I have a question for you. How does knowing you are never truly still change how you think about your own existence? Share your thoughts in the comments below. Your perspective makes this exploration richer for everyone. We have deconstructed the illusion of stillness and found a universe that is fundamentally dynamic. From the smallest quantum fluctuation to the architecture of spacetime, time itself is the engine of motion. Rest is relative, and the only constant is change. This is a different lens through which to view our own existence. We are not passive observers, but active participants in an unfolding cosmos. Every moment, we are traveling. Every second, we are part of a grand, cosmic motion. Thank you for taking this journey with me. You may have the sense that you can be perfectly still. That through sheer will, you can command every muscle, every fiber of your being, to just cease its movement. But you cannot. The very idea of stillness in a living thing is a profound and beautiful illusion. As you are now, your body is in a quiet, constant negotiation with gravity. A secret battle, fought on scales from the obvious to the atomic. In the next few minutes, we will journey into the invisible physics and hidden biology that keep you upright, and we will find that your stillness is one of the most dynamic processes you will ever experience. We tend to think of stillness as a default state. A rock on the ground. A book on a table. They seem to be at rest. We assume this is a passive state, an absence of activity. But physics tells a different story. That book is not simply resting, it is in a state of static equilibrium. And this state is anything but passive. Imagine two sumo wrestlers, perfectly matched, locked in a struggle. Neither moves. But are they inactive? No. They are exerting immense force, their efforts perfectly balanced, canceling each other out. The visible result is stillness, but the reality is a ferocious, silent effort. The book on your table is in a similar contest. Gravity is pulling it down, toward the center of the earth. The table is pushing back with an equal and opposite force, what physicists call the normal force. Gravity pulls, the table pushes. The forces are balanced, the net force is zero, and the book appears to be at rest. It is not an absence of force, but a perfect stalemate. But we can go deeper. If we were to look closer, past the surface of the book, down to the atomic level, the illusion of stillness would shatter. The atoms making up the book and the table are not still. They are cauldrons of energy. Each one is a nucleus surrounded by a cloud of electrons, all vibrating with thermal energy. They are shaking, oscillating, billions of times per second. Absolute stillness for an atom is only possible at absolute zero, a temperature colder than deep space, and a condition that is physically impossible to achieve. So even the most lifeless object we can imagine is, at its fundamental level, a storm of perpetual motion. Now, consider your body. You are not a simple object like a book. You are a collection of about 37.2 trillion cells, each a bustling city of its own. And you are balanced on two small points of contact with the ground. The idea that you could achieve a stillness greater than a book on a table is, when you think about it, impossible. Your stillness is not an absence of movement. It is the asterisk result of a million tiny movements, coordinated with breathtaking precision. It is an achievement, a constant, active process managed by the most sophisticated computer on the planet, your brain. Stillness is not your default state. Balance is. And balance is a full-time job. To understand why you cannot be still, we must first understand what standing truly is. In the language of physics, it is the act of keeping your body's center of gravity directly over your base of support. Imagine your center of gravity as a single point, usually around your lower abdomen. Your base of support is the area on the ground between your feet. As long as your center of gravity remains above this base, you are upright. If it strays, you begin to fall. This seems simple, but the human body's design makes it a monumental challenge. We are bipedal. Our base of support is small. And we are top-heavy. We are, in essence, a tall, segmented pole balancing on a narrow pivot. Think of a broomstick balanced on your palm. It requires constant, tiny adjustments. The moment those adjustments stop, it falls. You are that broomstick. Your body exists in a state of what is called postural sway. Even when you try to be as still as a statue, your body makes small, oscillating movements, swaying back and forth and side to side. This is not a flaw, it is the system working perfectly. Your body is perpetually falling, and then catching itself, over and over, many times each second. When your center of gravity drifts, receptors send a signal to your brain. In a fraction of a second, your brain commands muscles in your legs and torso, especially the powerful soleus muscles in your calves, to contract just enough to pull you back. This correction often overshoots, causing you to drift backward. A new signal, a new correction, and you are pulled forward again. This is a closed-loop feedback system, a constant dance between your body and the unyielding force of gravity. These movements are tiny, often just a few millimeters, but they are essential. Without postural sway, the smallest disturbance, a breeze, a deep breath, would send you toppling over. The muscular activity required for this is staggering. Over 600 muscles are involved in maintaining your posture. Even at rest, they are not resting. They are in a state of low-level tension, ready to act at a moment's notice. These corrections are so small and so fast, you are completely unaware of them. An unconscious ballet, directed by parts of your brain that never bother your conscious mind. Let's make this tangible. Stand with your feet apart. Try to be as still as you can. Now, close your eyes. Instantly, the task becomes harder. You will feel the sway become more pronounced. Your ankles will work, your calf muscles will tighten and release. This is your body's balancing act, suddenly exposed. By closing your eyes, you have removed one of the most critical streams of data for balance, forcing other systems to work harder. You are no longer just observing the illusion of stillness. You're feeling the dynamic reality underneath it. That wobble is not failure. It is the physical proof of your body's heroic, non-stop effort to keep you from falling. Closing your eyes makes balancing harder because it sidelines one of three critical sensory systems your brain relies on in its war against gravity. Think of them as an intelligence network, constantly feeding real-time data to your brain. First, the visual system, asterisk. Your eyes are your forward observers. They provide a constant stream of information about your body's position relative to the world. You see vertical lines in doorways, horizontal lines in the horizon. Your brain uses these external points to map your place in the environment. When you sway forward, the world in your vision appears to move slightly up. When you sway left, the world seems to shift right. Your brain detects these subtle flows as self-motion and issues immediate counter-commands to your muscles. This is why a disorienting pattern or a dark room can make you feel unsteady. Your visual system is being fed unreliable data. When you closed your eyes, you benched this system, forcing the others to pick up the slack. Second, the vestibular system, asterisk. Deep within your inner ear lies your second system, the vestibular system. This is your body's internal navigator, a gyroscope and accelerometer. It has nothing to do with hearing. Its only purpose is to detect motion and your orientation to gravity. It consists of two parts. First, three semicircular canals, filled with fluid. They are arranged at right angles to each other, like the three axes on a graph. When you rotate your head, the fluid sloshes and deflects tiny hair-like cells, telling your brain how your head is rotating. The second part is the otolith organs. These detect linear movement and, most critically, the constant pull of gravity. They contain tiny crystals that rest on sensory hairs. When you tilt your head, gravity pulls on these crystals, bending the hairs and signaling to your brain which way is down. This system is how you know if you are upside down with your eyes closed. When your body sways, the vestibular system detects that slight tilt, providing an objective measurement of your motion. It is the navigator that always knows which way is down. Third, proprioception, asterisk. This brings us to our third, and perhaps most mysterious, system, proprioception. Often called our sixth sense, it is the sense of where our body parts are in space without looking at them. It is the body's own internal awareness. It is why you can touch your finger to your nose with your eyes closed, or walk upstairs without staring at your feet. Embedded in your muscles, tendons, and joints are millions of sensory receptors. In your muscles, muscle spindles report how stretched a muscle is. In your tendons, Golgi tendon organs report how much force is being generated. And in the soles of your feet, pressure sensors report how your weight is distributed. As you sway forward, the pressure on the balls of your feet increases, your ankle angle changes, your calf muscles stretch. All this information streams to the brain, a detailed body map updated hundreds of times per second. This is the system that took over when you closed your eyes. With the visual system offline, your brain relied more heavily on the internal reports from your vestibular system and proprioception. The increased wobble you felt was this system working harder, making larger corrections because it was missing its long-range sensor. Together, these three systems, visual, vestibular, and proprioceptive, form a trinity of balance. They work in concert, constantly cross-referencing each other's reports to create a single, unified understanding of your body's state. It is this ceaseless flow of information that creates the powerful illusion you call stillness. So far, we have focused on the large, external struggle against gravity. But if we turn our attention inward, we find the illusion of stillness is shattered even more completely. Your body is not just moving to stay balanced, it is moving because it is alive. To be alive is to be in motion. Start with the obvious. Place a hand on your chest. That is your heart, a muscle contracting about once every second. With each beat, it sends a wave of blood through your body. This is not a gentle trickle. It is a powerful pulse that physically moves you, creating a tiny, rhythmic rocking motion through your entire frame. Now, take a breath. Your chest rises, your abdomen expands. Your diaphragm contracts, pulling air into your lungs and displacing your internal organs. This shifts your center of gravity. As you exhale, it all shifts back. This rhythmic displacement, 12 to 20 times a minute, is another source of constant, unavoidable motion. But the motion goes deeper. Even a muscle, at rest, is never truly silent. Hold your hand out as steady as you can. You might see a very fine tremor. This is not just nerves or caffeine, it is physiological tremor. It's a natural oscillation of your limbs, typically around 8 to 12 cycles per second in the hands, though this can vary. This tremor is a basic property of how your nervous system controls your muscles. The brain sends signals through motor neurons that fire in near synchrony, causing muscle fibers to twitch and relax in a rapid pattern. This is the hum of your body's engine at idle. And now, we must go to the final frontier of this motion. Past the organs, past the muscles, past the cells. About 60% of your body is water. Every one of your roughly 37.2 trillion cells is a small bag of water, filled with molecules. Picture a single drop of water under a microscope, with a few grains of pollen. The pollen grains do not sit still. They dance. They jiggle in a random, chaotic pattern. This is Brownian motion, and it is direct proof that matter is not static. The pollen is not alive. It is being moved by constant bombardment from invisible water molecules. At any moment, a pollen grain is being struck by millions of these molecules. If the collisions are balanced, it stays put. But by random chance, for a fraction of a second, more might hit from the left than the right, and the grain is shoved to the right. The result is a frantic, perpetual dance. This is happening right now, inside every cell of your body. The mitochondria, the ribosomes, the DNA itself, all are being constantly jostled by the thermal motion of water molecules. This is not a metaphor. It is the literal, physical reality of your existence. At the most fundamental level, you are a storm. A chaotic ballet of trillions of random collisions. True stillness is not just difficult. It is a physical and biological impossibility. So, where does this leave us? We have journeyed from the physics of a book on a table to the chaotic dance of molecules in our own cells. The conclusion is inescapable. You are physically incapable of being still. But this should not be a frustrating realization. It should be a source of profound wonder. We began with the idea of stillness as an absence of activity. We now see it as the opposite. The appearance of stillness in your body is an active, brilliant achievement. It is a symphony of unimaginable complexity, conducted by your brain. Think about it. Your body is an unstable structure built for agility, not stability. To keep it from falling, a network of systems, your eyes, your inner ears, and the nerves in your muscles, gathers intelligence from a gravitational field. This data streams to your brain, which issues thousands of corrective orders every minute to over 600 muscles. These muscles engage in a perpetual tug of war, a ballet of microscopic contractions, all to keep you centered. This is your postural sway, the invisible dance against the force that wants to pull you down. And while this external battle is waged, a universe of motion unfolds within. Your heart beats, sending shockwaves through your frame. Your lungs inflate and deflate, shifting your mass. Your nerves and muscles hum with a physiological tremor, a signature of life itself. And beneath it all, at the very foundation of your being, trillions of molecules inside every cell engage in the random, chaotic dance of Brownian motion. Stillness, then, is a harmony born from a million different movements. It is the asterisk dynamic equilibrium achieved when your brain masterfully coordinates the chaos. It is like listening to an orchestra. Isolate any single instrument, and you hear only motion and noise. But when the conductor brings them all together, the result can be a moment of seemingly perfect harmony. That is what your brain does. It is the conductor. Your body is the orchestra. It takes the swaying of your skeleton, the chatter of your sensory network, the thumping of your organs, and the fizz of your molecules, and from all that motion, it produces the illusion of a calm, stable, and still human being. This principle of dynamic equilibrium echoes across the universe. A star is a site of unimaginable violence, a continuous nuclear explosion, where the inward crush of gravity is perfectly balanced by the outward pressure of fusion. A galaxy maintains its spiral shape through a delicate balance of gravity and momentum. From the atom to the galaxy, stability is almost always the result of competing forces held in a tense, perfect balance. So the next time you find yourself standing, or simply waiting, take a moment. Try to feel it, the impossibly subtle sway, the faint hum of your own existence. Do not be frustrated by the movement you cannot quell. Instead, feel a sense of awe. You are not failing at being still. You are succeeding, miraculously, at being balanced. You are witnessing one of the most incredible performances in the natural world. Your stillness is not an empty silence. It is a symphony, and it is playing every second of every day for an audience of one. Thank you for joining me on this journey into the motion inside. If you enjoyed this exploration, please consider liking and subscribing for more. And wherever you are watching from, feel free to share. Until next time, keep exploring. You think your eyes are just passive windows to the world. You look at something, and it's just there. Your morning coffee, sitting perfectly still. A speck of dust hanging motionless in a sunbeam. We go through life with a simple, powerful assumption. To see the world is not to change it. Stillness is real. But what if that's fundamentally wrong? What if the universe has a rule so weird, so counterintuitive, that it shatters our entire idea of a quiet, stable reality? The laws of physics actually disagree with our common sense. They say that the act of looking at something isn't passive. It's a physical interaction, a force, and it destroys the very stillness you thought you saw. We're about to zoom in on reality, way past what our eyes can see, to find a hidden truth about the cosmos. We'll start with jiggling atoms, zoom out to the cosmic expressway, and then dive headfirst into the bizarre quantum realm, where observing reality doesn't just see it, it helps create it. You're about to find out why the simple act of looking at something instantly and unavoidably moves the world. So, why do we believe in stillness in the first place? Well, our brains are incredible survival machines, but they're not truth machines. They're filters. Think about it. Right now, your ears are getting hit with all sorts of sounds. The hum of your computer, a car outside, the air in the vents. Your brain just tunes most of it out so you can focus. Your eyes do the same thing. They aren't showing you everything, they're building a stable, usable model of the world for you. If you actually saw every single jiggle, every vibration, every tiny motion happening constantly all around you, the world would be an incomprehensible, shimmering chaos. You couldn't pick up a glass of water because you'd be mesmerized by the frantic dance of its molecules. A friend's face would just be a vibrating cloud of atoms. So, our brains create a very useful lie, the lie of stillness. This idea of a static world is baked into our history. The ancient Greeks argued that all change is an illusion. For most of human history, the Earth was the unmoving center of the universe. It's our intuitive reality. The ground feels solid. The chair you're in feels stationary. Our senses and our language are built on this foundation of stillness. We think of observation as a one-way street. Light hits an object, goes into our eye, and we passively get the information. We're the audience, the universe is the show. We assume we can know something's position or state without affecting it. But imagine you want to check the temperature of some soup. You stick a thermometer in. You think you're just measuring the soup's temperature, but by putting a colder thermometer in, you've actually cooled the soup down, just a tiny bit. The act of measuring changed the thing you were measuring. That's a small example, but it's a crack in the foundation of our passive observer illusion. It hints at a deeper truth. Observation isn't some magical, detached act. It's a physical process. To see something, something has to travel from that object to your eye. Usually, that something is light, made of countless tiny packets of energy called photons. When a photon bounces off an object and hits your eye, it carries information. But that bounce? It's a collision. It's a physical interaction that gives the object a tiny, usually negligible, kick. For big things, like a bowling ball or a grain of sand, this kick is so small that we can totally ignore it. The bowling ball doesn't care. And so our illusion of being a passive observer holds up. We check the tire pressure in a car, and even though a little air escapes, changing the pressure, the effect is so tiny we don't think about it. But what happens when we stop looking at bowling balls and start looking at the fundamental building blocks of reality? What happens when the thing we're looking at is so small that the gentle tap of one photon isn't a tiny nudge, but a catastrophic shove? This is where our comfortable illusion gets completely obliterated. This is where we leave common sense behind and enter the universe as it truly is. A place of perpetual, unavoidable motion. Imagine you could shrink down, way, way down. The room around you becomes a city. The table becomes a vast plain. As you get closer to its surface, you realize it isn't still at all. It's vibrating. It's humming with a chaotic energy, like a swarm of invisible bees trapped inside. This isn't science fiction. This is the reality of thermal motion. Everything you see, unless it's cooled to the impossible temperature of absolute zero, is seething with internal motion. The feeling of hot or cold is just our large-scale perception of this microscopic chaos. Temperature is just a measure of the average motion energy of atoms and molecules. The hotter it is, the more violently its parts are shaking and crashing into each other. That still coffee cup? Its atoms are jiggling in place trillions of times a second. The still air in the room? It's a hurricane of nitrogen and oxygen molecules zipping around at hundreds of meters per second, hitting each other and you billions of times a second. You don't feel them as individual pokes, just as steady air pressure. Your own body is a universe of motion. Every atom is part of a relentless microscopic dance. This hidden world of motion was first glimpsed in 1827 by a Scottish botanist, Robert Brown. While looking at pollen grains in water under a microscope, he saw something weird. The grains weren't sinking, they were darting and zigzagging as if they were alive. At first, he thought he'd found some basic life force. But then he tested other things: dust, soot, even tiny chips of glass. They all did the same erratic dance. He even used dust trapped in quartz for thousands of years, proving it had nothing to do with life. This became known as Brownian motion. For decades, it was a mystery. What was this invisible force making things jitterbug? The answer, finally proposed by Albert Einstein in 1905, was profound. There was no mysterious force. The pollen grains were moving because they were being constantly bombarded by the invisible, fast-moving molecules of the water itself. Imagine a giant beach ball in a mosh pit of thousands of toddlers. Each individual push is tiny. But if, by pure chance, more toddlers happen to push from the left at the same time, the ball will lurch to the right. A second later, a random group of pushes from behind sends it surging forward. The ball's large, visible, random movement is the result of thousands of tiny, invisible, random collisions. That's exactly what Robert Brown was seeing. The pollen grain was the beach ball, and the water molecules were the toddlers. Einstein's explanation was huge. It was one of the first real proofs that atoms and molecules actually existed. At this scale, looking at the pollen doesn't create the motion. The motion is already there because of heat. But by choosing to look closely, we shatter the illusion of stillness our naked eye provides. The only way to truly stop all this jiggling is to reach absolute zero, 0 Kelvin. That's the theoretical point where all classical atomic motion stops. But the laws of thermodynamics tell us that reaching absolute zero is physically impossible. So, in our universe, a baseline of constant thermal motion is a non-negotiable fact of reality. Nothing is ever truly still. So, the first reason you can't look at something that's perfectly still is that nothing is ever still to begin with. The stillness you see is just a large-scale illusion. But this is just the first layer. What happens if we zoom out instead of in? Let's go back to your chair. You feel still. The room is still. The city is still, right? Well, you're on a planet that's spinning on its axis. Right now, you're moving at up to 1,670 kilometers per hour. You don't feel it because everything around you, the air, the building, is moving with you. But that's just for starters. The Earth is also hurtling around the Sun at a staggering 107,000 kilometers per hour. That's fast enough to cross a continent in a few minutes. Still feel nothing. And the Sun? Not still either. Our entire solar system is being dragged on a grand tour around the Milky Way galaxy at a mind-boggling 828,000 kilometers per hour. The last time Earth was in this spot, dinosaurs were just getting started. And the Milky Way itself? Also on the move. It's hurtling through the universe, pulled by other galaxies in our local group, which is itself being pulled towards a massive gravitational anomaly called the Great Attractor. Our galaxy is careening through space at about 2.1 million kilometers per hour. So, as you sit there feeling perfectly still, you are simultaneously spinning, orbiting, and being flung through the cosmos at incredible speeds. Stillness, it turns out, is relative. This was one of Einstein's biggest insights. There is no absolute rest in the universe. You can't point to a spot and say, this is the center. The one true point of stillness. It doesn't exist. Motion can only be described relative to something else. You are still relative to your room. But you're moving at 107,000 kilometers per hour relative to the Sun. So which is your true speed? The question is meaningless. They're all equally valid. And how do we know we're moving? We observe. Astronomers noticed that nearby stars seem to shift against the backdrop of distant stars as Earth goes around the Sun. This is called parallax. You can see it right now. Hold your thumb out at arm's length. Close your left eye and look at your thumb. Now switch eyes. Your thumb appears to jump back and forth against the background. That jump is parallax. Okay, but you might be thinking, what about the cosmic microwave background? The CMB is the faint afterglow of the Big Bang, a sea of radiation filling all of space. Couldn't we call that the universe's true rest frame? If we're moving relative to it, we should see the light in front of us get slightly hotter, and the light behind us get slightly cooler. And guess what? We do. Measurements show our solar system is moving at about 370 kilometers per second relative to the CMB. So is that it? Have we found absolute rest? Not really. The laws of physics work exactly the same whether you're at rest with the CMB or flying past it. It's a convenient reference point for cosmologists, but it's not a universal anchor of stillness. So the illusion of stillness is shattered on a cosmic scale, too. We are never still. We're on a cosmic carousel, and looking out at the stars is what makes us aware of the ride. But we have one more level to go. The deepest, weirdest level of all. This is where looking doesn't just reveal motion. This is where looking creates it. We've seen the thermal dance of atoms and the cosmic rush of galaxies. Now, let's take the final plunge into a realm so bizarre that our everyday intuition completely fails. Welcome to the quantum world. In our world, a baseball has a definite position and a definite speed. But in the quantum realm of electrons and photons, the rules are different. Down here, particles aren't tiny baseballs, they're more like clouds of possibility. This is wave-particle duality. A particle like an electron, when you're not looking at it, doesn't have a precise location. It exists as a wave of probability, spread out over a region. Think of a spinning coin. While it's in the air, is it heads or tails? the question doesn't make sense. It's in a superposition of both. Only when it lands, when it's measured, does it pick one. An unobserved electron is like that spinning coin. It's a wave of potential places it could be. This is a demonstrable fact, proven by the most famous experiment in physics, the double-slit experiment. Imagine a wall with two thin slits. You fire electrons, one by one, at the wall. Behind it, a screen records where they land. If you were firing paintballs, you'd expect two simple bands on the screen. But when you do this with electrons, and you're not watching which slit they go through, they don't form two bands. They form an interference pattern, a series of many alternating bands, which can only be made by waves interfering with each other. This means each single electron, by itself, goes through both slits at the same time, behaving like a wave and interfering with itself. But here's where it gets insane. This is where looking instantly moves the world. The physicists who saw this were baffled. They said, let's check. Let's put a detector by the slits to see which one each electron goes through. The moment they turn on the detector, the moment they observe the electrons, the interference pattern vanishes. Gone. In its place are two simple bands, just like the paintballs. By looking, they forced the electron to make a choice. It was no longer a wave of possibility. It was forced to act like a particle and pick a slit. The act of observation collapsed the wave function and changed the outcome. Now, looking here doesn't mean a person's consciousness. It means any physical interaction with a detector. To find out which slit the electron went through, the detector has to interact with it, maybe by bouncing a photon of light off it. And that physical interaction is what changes everything. This brings us to the ultimate source of all this weirdness. Werner Heisenberg's uncertainty principle. Formulated in 1927, this principle is a fundamental speed limit on what we can possibly know about the universe. It says there are pairs of properties, like a particle's position and its momentum, that cannot both be known with perfect accuracy at the same time. The more precisely you measure one, the less precisely you know the other. It's not a flaw in our tools, it's a fundamental property of nature. Imagine you want to find an electron's exact position. To see it, you need to hit it with something, like a photon. To pinpoint its position accurately, you need a high-energy, short-wavelength photon. So you fire your high-energy photon. Bang! It hits the electron and bounces to your detector, telling you exactly where the electron was. But by hitting it with a high-energy photon, you've given the electron a massive, unpredictable kick. You now know its past position perfectly, but you have no idea where it's going or how fast. What if you try the opposite? To measure its momentum precisely, you'd use a very low-energy photon. This would barely disturb its momentum. But a low-energy, long-wavelength photon is like trying to find a single pea in a dark room by poking around with a giant pillow. You can't get a precise location. By measuring the momentum accurately, you've lost track of the position. This is the trade-off at the heart of reality. The uncertainty in position times the uncertainty in momentum must always be greater than or equal to a tiny number called Planck's constant. You can squeeze one uncertainty down, but the other one will always balloon up. This is the ultimate reason why looking at something instantly moves it. If you want to confirm something is still, meaning it has zero momentum and a definite position, the uncertainty principle says no. It's forbidden. The very act of confirming its position with perfect precision would make its momentum infinitely uncertain. In other words, looking at it to confirm it still would give it such a violent kick it would fly off in a random direction. You can never find a particle at rest, because the act of finding it gives it motion. So, from the jiggling of atoms to the quantum shudder of an electron, the idea of a truly still universe just evaporates. The act of looking is never passive. It's a physical interaction that reveals, defines, and at the deepest level, creates motion. If this has shifted your perspective on reality, consider subscribing. We tackle these kinds of mind-bending questions every week. We started with a simple idea. The world is still, and we're just watching. We've gone from the classical to the cosmic to the quantum, and at every level, that idea has been shattered. We found that everything with a temperature, which is everything above the impossible to reach absolute zero, is seething with the thermal motion of its atoms. Stillness is a macroscopic illusion. We found that in the vastness of space, there is no absolute rest. We are all cosmic wanderers, and our dizzying speed is only revealed when we observe our motion relative to other things. And finally, in the quantum realm, we found the most profound truth. There's a fundamental trade-off between knowing where something is and where it's going. The act of observing a particle's position to confirm its stillness is the very act that gives it motion. So the next time you sit perfectly still, appreciate the beautiful lie your brain is telling you. Remember, you're a collection of trillions of vibrating atoms, sitting on a rock that's spinning and hurtling through the cosmos at incredible speeds. And remember that the very stuff you're made of exists in a constant, shimmering state of quantum uncertainty, where stillness isn't just unlikely, it's fundamentally impossible. Stillness was never an option. You are, and always have been, in motion. What object will you never see as still again? Let me know in the comments below. And as always, thanks for watching. Why does anything move? It's a question so simple, it feels as if it belongs to childhood. Yet, it is a question that has quietly occupied thinkers for millennia. Look around you for a moment. A leaf skitters across the pavement. Clouds drift overhead. The Earth itself is in a constant, dizzying spin, moving through space at a speed that is difficult to imagine. And when we look out into the cosmos, we see the same story, written on the grandest of scales. Planets orbit stars, stars turn on their axes, and entire galaxies pirouette in a slow, majestic dance that has lasted for billions of years. Nothing, it seems, is ever truly still. But why? Why this incessant, universal motion? Why doesn't the universe just stop? Our everyday experience suggests that all motion is temporary. You push a ball, and it eventually comes to a halt. You spin a top, and it wobbles to a standstill. But what if this is an illusion? What if the universe is governed by a single, unbreakable rule that makes true stillness impossible? A law more fundamental than we can imagine, one that dictates that motion, once started, must continue. If you have ever watched a figure skater perform a spin, you have seen this rule in action. She begins with her arms outstretched, rotating at a steady, graceful pace. Then, she pulls her arms in close to her body, and suddenly, her spin accelerates into a stunning, high-speed blur. No one has given her another push. The energy for that dramatic increase in speed came from somewhere deep within the laws of physics itself. That seemingly simple act is a perfect demonstration of the universe's one unbreakable rule. It is a rule that acts as a cosmic accountant, meticulously tracking every bit of rotational motion, ensuring none is ever lost. And this law is the secret to why the universe avoids stopping. Today, we will go on a journey to uncover this cosmic law. Welcome. If this kind of calm exploration into the cosmos helps you unwind, consider liking the video and subscribing. We will travel from the familiar world of spinning tops to the heart of collapsing stars and the grand architecture of galaxies. We'll go back to the very first moments of the universe to find the origin of all this cosmic spin and discover that the movement of our own Milky Way is an ancient echo of the universe's birth. By the end, we may come to see that stillness is the real myth, and motion is the fundamental reality. Our first task is to dismantle a powerful idea, one ingrained in us from the moment we first watch a toy car slow to a halt. The idea that everything naturally comes to rest. On the surface, it makes sense. Friction is the great thief of motion in our world. A rolling ball loses its energy to the ground as its molecules rub against the surface, generating tiny amounts of heat until its momentum is spent. A spinning top is betrayed by the air itself, as molecules of nitrogen and oxygen create a drag that slowly steals its rotational energy. Even the tides of our oceans, sloshing back and forth, exert a frictional drag on the Earth. The effect is almost imperceptible, yet it is there. Our planet's rotation is slowing, by roughly 1.7 milliseconds each century, transferring that rotational energy to the Moon, which inches away from us by a few centimeters every year. So, if everything we see is slowed by these forces, why would the universe at large be any different? The answer lies in the sheer emptiness of space. The cosmos is the most perfect vacuum we can imagine, a realm where friction and air resistance are almost non-existent. An object set in motion in the void between stars can travel for billions of years without anything significant to slow it down. A spinning asteroid or planet can maintain its rotation for eons, undisturbed. In this environment, the true nature of motion is revealed. It doesn't naturally die out. It persists. But the prohibition against stillness goes even deeper, down to the very fabric of reality itself. Let's imagine we could somehow eliminate all external forces. We could isolate a single atom in a perfect vacuum and cool it down, draining away its thermal energy, bringing it as close as we can to absolute zero, the theoretical temperature where all classical motion should cease. Surely, then, it would be still. But it wouldn't. Even at absolute zero, the atom would continue to vibrate with a minimum, unremovable amount of energy. This is not a failure of our technology. It is a fundamental command from the strange world of quantum mechanics. This residual motion is called zero-point energy, and it is a direct consequence of one of the most famous principles in all of science, the Heisenberg uncertainty principle. Werner Heisenberg discovered in 1927 that there is a fundamental limit to what we can know about a particle. You can know its position with great precision, but its momentum then becomes uncertain. Conversely, you can measure its momentum exactly, but its position becomes a complete blur. You can never know both with perfect accuracy at the same time. If our atom at absolute zero were to become perfectly still, we would know its momentum with absolute certainty, zero. According to the uncertainty principle, its position would then have to be infinitely uncertain. It would be everywhere in the universe at once, which is, of course, impossible. To avoid this paradox, the particle must always possess a little uncertainty in its momentum, which means it must always be moving, just a tiny bit. This constant, unavoidable quantum jitter is the universe's ultimate decree against absolute rest. From the smallest possible scale, reality is built on a foundation of ceaseless motion. Stillness is not just difficult, it is fundamentally forbidden. We have established that nothing seems to be truly still. But is all this motion just random chaos, or is there a governing principle, an architect's blueprint that organizes this cosmic dance? The answer lies in one of the most elegant laws in physics, the law of conservation of angular momentum. For centuries, brilliant minds sought to understand the motions of the heavens. Kepler plotted the paths of the planets, and Newton formulated his laws of motion and gravitation. They could predict where a planet would be, but the deeper, why behind the persistence of its orbit remained elusive. The conservation laws were seen as useful mathematical tricks, but their true significance was a mystery. It wasn't until the early 20th century that a quiet revolution in physics, led by the brilliant German mathematician Emmy Noether, revealed the profound truth. In 1915, she published a theorem that has been described as one of the most beautiful in all of physics. She proved that conservation laws are not accidents. They are a direct consequence of the symmetries of the universe. A symmetry is a transformation you can make that leaves the laws of physics unchanged. For example, the laws of physics do not change over time. An experiment conducted today should yield the same result tomorrow. Noether proved this time symmetry is precisely why energy is conserved. Similarly, the laws of physics are the same everywhere, which is called spatial symmetry, and this gives us the conservation of linear momentum. And then there is rotation. The laws of physics do not depend on which way you are facing. They are the same whether you look north, south, east, or west. This is rotational symmetry. M. Noether's theorem shows that this very symmetry, the fact that the universe has no preferred direction, is the reason angular momentum is conserved. This elevates the law from a mere observation to a fundamental pillar of reality. It is woven into the very geometry of spacetime. So what is angular momentum? It is the rotational equivalent of regular momentum. For a spinning object, angular momentum is a measure of how much spin it has. Mathematically, it is often written as L equals I omega. L is the angular momentum. I is the moment of inertia, which measures how spread out the object's mass is from its axis of rotation. And omega is its angular velocity, or how fast it's spinning. The law of conservation of angular momentum states that in a closed system, the total angular momentum, L, must remain constant. It cannot be created or destroyed. This is where we return to our figure skater. When she is spinning with her arms outstretched, her mass is distributed far from her center. Her moment of inertia, I, is large. To maintain her angular momentum, her rotational speed, omega, is relatively slow. But when she pulls her arms in, she drastically reduces her moment of inertia. Her mass is now concentrated close to her axis of spin, so I becomes very small. Because the universe acts as a perfect accountant, the total angular momentum, L, must stay the same. Since I has gone down, the only way for the equation to balance is for omega, her spin speed, to go up. She spins faster not because she's exerting a new force, but because the universe is rigidly enforcing a conservation law. This isn't a suggestion. It is a non-negotiable command that every spinning system in the universe must obey. Now, let us take this principle of the skater's spin and apply it to the cosmos. We are about to see how this simple law sculpts the universe, transforming chaotic clouds of gas into the elegant, structured forms we see in the night sky. Our journey begins with the birth of a star system. Imagine a vast, cold cloud of gas and dust, light years across, floating in the interstellar medium. This cloud is not perfectly still. It has a slight, almost imperceptible net rotation, a ghost of a spin inherited from the turbulent motions of the galaxy. Over millions of years, gravity begins its patient work, gently tugging on the particles, pulling them closer together. The cloud starts to collapse. As the cloud contracts, we see the figure skater effect on a cosmic scale. The moment of inertia, I, shrinks as the material falls inward. To keep the total angular momentum constant, the cloud's rotational speed, omega, must increase dramatically. What began as a slow drift accelerates into a furious spin. This rapid rotation creates an outward force that resists gravity's inward pull, flattening the collapsing cloud into a rapidly spinning disk, known as a protoplanetary disk. This is the origin story of our solar system. At the dense, hot center of this disk, the Sun was born. In the swirling material around it, dust and ice stuck together, growing into pebbles, then boulders, and finally, the planets. The fact that all the planets orbit the Sun in the same direction and on roughly the same flat plane is a direct, fossilized record of the angular momentum of that initial gas cloud. Earth's journey around the Sun is a form of angular momentum. It cannot simply stop and fall into the Sun, because that would violate this fundamental law. We see this law at work elsewhere. Jupiter's Great Red Spot is a colossal storm larger than Earth. Its incredible longevity. We have observations of a great storm in that spot stretching back some 400 years. Is a testament to its enormous angular momentum. It is a self-contained vortex that, in the absence of significant friction, simply persists. Now, let's zoom out further, to the scale of galaxies. The breathtaking spiral arms of the Milky Way are not just beautiful, they are monuments to the conservation of angular momentum. Like a solar system, a galaxy begins as a gigantic, slowly rotating cloud of primordial gas and dark matter. As this vast halo of matter collapses under its own gravity, it spins up, flattening into the magnificent disk structures we see today. The billions of stars within it are all participating in this grand, coordinated rotation, each carrying a piece of the galaxy's total angular momentum. What if this law could be broken? The consequences would be profound and unraveling. Planets would lose their stable orbits and begin a slow spiral into their stars. The great storms on Jupiter would dissipate. But the most dramatic effect would be on galaxies. Without the support provided by rotation, the majestic spiral disks would collapse into chaotic, formless swarms of stars. The universe would lose its shape, its structure, its character. The universe we know, dynamic and alive with structure, exists because it spins. We've seen how the conservation of angular momentum sculpts and sustains the universe. But this brings us to a deeper question. If angular momentum can't be created from nothing, where did all this cosmic spin come from in the first place? To answer this, we must journey back to the very beginning of time. For a long time, it was thought that the universe began in a perfectly smooth, uniform state. If everything started out perfectly symmetric, it is hard to see how any large-scale rotation could develop. But we now know the early universe was not perfectly smooth. At the quantum level, it was a seething soup of energy. The key, once again, lies in quantum mechanics. In the instant after the Big Bang, the universe was unfathomably hot and dense. The vacuum of empty space was not truly empty, but filled with quantum fluctuations, tiny, spontaneous changes in the amount of energy at a point in space. These fluctuations were chaotic, creating infinitesimally small variations in density and motion. Imagine the very fabric of spacetime, in its first moments, trembling with tiny, fleeting asymmetries. Normally, these microscopic variations would average out to nothing. But in the first fraction of a second, the universe underwent a period of hyperacceleration known as cosmic inflation. This explosive expansion did something incredible. It grabbed those fleeting, microscopic quantum asymmetries and stretched them to unimaginable, astrophysical scales. A tiny variation in density was inflated to become the seed of a future supercluster of galaxies. And tiny, random variations in motion were stretched across millions of light years, imparting a slight but definite net angular momentum to vast regions of matter. As these regions later collapsed, tidal forces from neighboring clumps of matter would have also exerted torques, further spinning up these protogalactic structures. This is the origin story of cosmic spin. It was born from the inherent randomness of quantum mechanics, magnified to cosmic proportions by the explosive growth of the early universe. Scientists are now finding evidence for this ancient spin. Some studies of thousands of galaxies suggest a slight preference for a certain direction of rotation, a handedness, to the universe, which could be a fossilized remnant from the very beginning. Discoveries of enormous cosmic filaments that appear to be rotating provide strong evidence that angular momentum was imprinted on the cosmic web itself. So when you look up at the Milky Way, you are witnessing a direct echo of the Big Bang. The majestic rotation of our galaxy is a preserved piece of quantum history, a memory of one of the first, tiniest asymmetries that ever occurred in the fabric of our universe. This unbreakable rule has guided the universe from its quantum origins to its galactic present. But what about the future? As we look ahead, into the deepest reaches of time, will the universe eventually grind to a halt? The evidence suggests the answer is no. The universe's commitment to motion appears to be eternal, driven first by the continued expansion of the universe itself. This expansion, which is accelerating due to dark energy, ensures the cosmos will not collapse back on itself. Instead, the most widely accepted scenario for its ultimate fate is known as the Big Freeze, or heat death. In this distant future, trillions of years from now, star formation will cease. Stars will burn out, leaving behind a graveyard of white dwarfs, neutron stars, and black holes. Even in this cold, dark, and seemingly dead universe, motion will persist. The remnants of planets will continue to orbit their dead stars, and these dead solar systems will continue to orbit the central black holes of their faded galaxies, all still conserving their angular momentum. Eventually, even these structures will dissolve. But black holes provide the ultimate test for our unbreakable rule. When two black holes merge, the resulting, larger black hole has a spin precisely determined by the spins and orbital momentum of the two that created it. Even at the edge of reality, the cosmic accountant is on the job. We have even confirmed a prediction of Einstein's general relativity from over a century ago known as frame dragging, where the intense spin of a massive object literally twists the fabric of spacetime around it. In the era of the Big Freeze, black holes will slowly evaporate through Hawking radiation. But the particles they emit will still carry energy and momentum. Motion will continue, just in a different form. The second law of thermodynamics tells us that the universe always moves toward greater disorder. A static, unchanging universe would be a universe at maximum entropy. This final, heat death, is not an end to motion, but rather the end of useful motion. Motion will become a uniform, featureless hum. From the first quantum flicker to the final whisper of an evaporating black hole, the rule remains unbroken. The universe was born in motion, it lives in motion, and it will die in motion. Stillness is, and always will be, the one true impossibility. We began with a simple question: why does everything move? Our journey took us from the grace of a spinning skater to the strange realities of the quantum realm and back to the birth of the cosmos. We discovered that our perception of stillness is a local illusion, and that at the deepest level, the universe forbids absolute rest. At the heart of it all, we found the architect, the law of conservation of angular momentum. This is not just a rule, but a consequence of the universe's fundamental symmetry, as revealed by the brilliant Emmy Noether. This single, elegant principle explains why gas clouds form spinning disks, why planets maintain their orbits, and why galaxies pirouette through the ages. It is a cosmic memory keeper, preserving the initial asymmetries of the Big Bang. So, the next time you stir your coffee and watch the liquid swirl, or see leaves caught in a gust of wind, take a moment. Realize that you are replaying a fundamental act of creation. You are participating in the same cosmic dance that formed the stars and set the galaxies spinning. Motion is not just a law of physics, it is the signature of reality. It's the persistent, unending pulse of a dynamic cosmos, and the very reason we are here to witness it. If this kind of calm exploration into the world around us helps you unwind, consider subscribing and joining our community. And for those who wish to support our work in creating these explorations, we have a Patreon where you can get involved. Your support makes these journeys possible. There is a feeling you have right now, a sense of complete and total stillness. It feels real. It feels solid. It is the simple sensation of you, sitting here, unmoving. But this sensation is a profound and elaborate illusion. It is perhaps one of the most significant, and most necessary, fictions your mind has ever constructed. As you sit there, feeling perfectly still, you exist on a planet that is spinning on its axis at roughly 1,040 miles per hour at the equator. That same planet is orbiting a star at an astonishing 67,000 miles per hour. That entire solar system is being carried around the center of our galaxy at a speed approaching 500,000 miles per hour. And the galaxy itself, our Milky Way, is hurtling through the universe at a velocity of approximately 1.3 million miles per hour, relative to the background radiation left over from the beginning of space and time. You are not still. You are a passenger on a cosmic vessel, navigating multiple, simultaneous vectors of motion. And this does not even begin to touch on the chaos occurring within you. The very atoms that make up your body, the chair you're sitting on, the air you are breathing, none of it is truly at rest. Every particle is a storm of vibration, a furious, ceaseless dance. So here we arrive at the paradox that governs our existence. Physical reality is an endless storm of motion, from the smallest quantum fluctuation to the grandest cosmic expansion. Yet, the mind experiencing this reality requires a belief in stillness. Not as a physical state, which is an impossibility, but as a psychological anchor. A fixed point, an illusion that is absolutely essential for clarity, for sanity, and for survival. This is not a story that denies physics. This is a journey to understand why our brain evolved to ignore it. We will explore the universe's constant motion. Then, we will turn inward, to the quiet miracle of the human mind, to understand why it creates this fiction of stillness. And finally, we will discover how you can consciously use this paradox, this manufactured calm, to navigate the chaos of modern life. To truly grasp the paradox, we first need to confront the storm. We need to look at the universe as it actually is. A place where the concept of rest is a convenient fiction. This journey begins not in the vastness of space, but in the very substance of your being. If you hold up your hand, it appears solid. It feels solid. Yet what you are perceiving as solid is an illusion generated by statistics and the limits of our senses. If we could zoom in, past the skin and cells, down to the atomic level, the picture changes entirely. Every atom in your hand is a nucleus surrounded by a cloud of electrons, and these atoms are in constant, ceaseless vibration, driven by thermal energy. Every object with a temperature above absolute zero, which is every object in the universe, is humming with this atomic motion. A coffee mug is better imagined not as a single, static object, but as a swarm of trillions of particles vibrating with such incredible speed and coordination that they produce the asterisk illusion of a stable shape. But it gets stranger. If we were to cool something down to absolute zero, minus 273.15 degrees Celsius, surely, then, things must stop. They do not. Because of a fundamental rule of quantum mechanics, the Heisenberg uncertainty principle, perpetual motion is mandatory. The principle states that you cannot simultaneously know both the exact position and the exact momentum of a particle. If an atom were to become perfectly still, we would know its momentum, zero, and its position with perfect certainty, an act forbidden by the laws of the universe. Therefore, even at the coldest possible temperature, particles retain a minimum amount of vibrational energy known as zero-point energy. It is the baseline hum of the cosmos, an energy that exists even in the vacuum of empty space. It is the universe's fundamental refusal to ever be truly quiet. Even that empty space is not empty. At the smallest conceivable scale, the Planck length, spacetime itself is theorized to be a roiling, bubbling, quantum foam. Here, for impossibly brief moments, pairs of virtual particles are thought to flash into existence from nothing and then annihilate each other, driven by quantum fluctuations. There is no such thing as a true void. From the core of your bones to the vacuum of deep space, everything exists in a state of perpetual, frenetic motion. Now, let us zoom out. You are sitting in a room, feeling stationary. We can stack these motions to appreciate the sheer velocity of your stillness. First, the Earth's rotation. At the equator, you are moving at approximately 1,040 miles per hour, or 1,670 kilometers per hour. Second, the Earth's orbit. Our planet travels at an average speed of 67,000 miles per hour to complete its journey around the Sun. This is fast enough to cross the entire diameter of the Earth in about 7 minutes. Third, our solar system's orbit. The Sun, along with its planets, orbits the center of the Milky Way galaxy in a journey that takes over 200 million years to complete one lap. The speed required is a staggering 450,000 to 500,000 miles per hour. Fourth, the motion of our galaxy. The Milky Way is part of a local group of galaxies being pulled by gravity towards a massive anomaly known as the Great Attractor. When you combine these galactic movements, our galaxy is traveling through the universe at an estimated speed of 1.3 million miles per hour, or about 600 kilometers per second, relative to the cosmic microwave background, the afterglow of the Big Bang. So, as you feel the weight of your body in your chair, you are on a spinning ball that is hurtling around a star, which is screaming around a galactic core, which itself is being flung through an expanding universe. The raw physics of the situation is overwhelmingly violent. If you were consciously aware of even a fraction of this motion, it would be a sensory nightmare. So why aren't you? Why does the world feel so stable and solid? The answer is found within the human brain. Your brain is not a passive receiver of information. It is an active filter. Its primary job is not to show you reality in all its raw detail. Its primary job is to create a model of the world that is useful for survival. To do that, it has to edit, simplify, and abstract. The reason you don't feel the Earth's spin or its orbit is because of relative motion. Everything in your immediate vicinity, the room, the building, the atmosphere, is moving along with you at the same constant velocity. Your senses have no external reference point to register the movement. Much like being on an airplane in smooth air, the world appears stationary. But the filtering goes much deeper. At the atomic level, your brain simply could not process the volume of information. The buzz of trillions of vibrating atoms would be a deafening, paralyzing roar. To function, to pick up a cup, to have a thought, your brain performs an act of simplification. It averages out all that microscopic chaos and presents you with a single, stable, unified concept: cup. This is the birth of the illusion of stillness. It is a necessary abstraction of reality. Your brain creates a functional user interface for the universe. An icon on a computer screen is not the complex code it represents, but it allows you to interact with that code. In the same way, the stillness of the world you perceive isn't the physical truth, but it's the icon your brain creates so you can navigate the impossibly complex code of reality without becoming overwhelmed. This manufactured stillness becomes the bedrock of your psychological world. It is the quiet background that allows you to separate signal from noise. Without this perceived stillness as a fundamental anchor, the mind would be adrift in the storm of physical reality. The sheer sensory input of the universe's true nature would create a state of constant, overwhelming anxiety. This is the core of the paradox. The universe never stops, but your mind must pretend it does to create a space for sanity. The chaos is real, but the stillness is essential. And now, we turn to how the brain doesn't just create this stillness for basic survival, but how it actively seeks it out to heal, create, and become more resilient. If the illusion of stillness is the brain's default survival strategy, the conscious cultivation of stillness is one of its most advanced capabilities. The brain didn't just evolve to filter out chaos. It evolved a deep, biological need for moments of profound inner quiet. This is a neurological necessity. When we intentionally seek stillness, we are activating powerful mechanisms designed to restore and repair the very architecture of our minds. If you have ever tried to sit quietly, you may have noticed that the mind goes wild with thoughts, worries, and memories. This internal chatter is not a personal failing. It is the signature of a specific brain circuit known as the default mode network, or DMN. The DMN is a collection of brain regions that becomes highly active when we are not focused on an external task. It is what the brain does when it is doing nothing. This network is crucial for self-reflection and planning, but in the modern world, an overactive DMN can become a liability. It is the engine of rumination, the repetitive, negative thinking that is a hallmark of anxiety and depression. When we say our mind is racing, We are often describing an overactive DMN. Practices like mindfulness meditation are not about stopping thoughts, which is impossible. They are about changing our relationship to them by training other brain circuits, like the salience and executive networks, to take a more active role. Neuroimaging studies show that with practice, meditation can quiet the DMN and change its connectivity, reducing its unhealthy, looping activity. You are, in a very real sense, training your brain to turn down the volume on its own internal noise. The chaos of the world is also a physiological problem. Our body's sympathetic nervous system, our fight or flight response, prepares us for threats by flooding the body with cortisol and adrenaline. While useful in short bursts, chronically elevated levels can suppress the immune system and increase inflammation. The counterbalancing system is the parasympathetic nervous system, PNS, our rest and digest mode. It lowers heart rate, promotes digestion, and brings the body back into a state of balance, or homeostasis. Practices that promote stillness are a way to consciously influence this parasympathetic switch. Studies have shown that even brief periods of silence can be more effective at lowering heart rate and blood pressure than listening to relaxing music, directly engaging this calming response. Mindfulness practices have also been shown to significantly reduce levels of the stress hormone cortisol. This biological reset is illustrated by the human heart. Between each beat, there is a tiny pause, the diastolic phase, where the heart muscle relaxes. Without these micro pauses of stillness, the heart would fail. It is a perfect biological analogy for our psychological need for stillness. Constant action without restorative pauses leads to breakdown. Perhaps the most startling discovery is that stillness may physically change the brain's structure. We now know the brain is plastic, capable of reorganizing itself and even growing new neurons, a process called neurogenesis. A landmark 2013 study on mice found that 2 hours of silence per day led to the development of a significant number of new neurons in the hippocampus, a brain region vital for learning, memory, and emotional regulation. While this specific research is in animals, and human evidence remains preliminary, it suggests that a quiet environment may provide the necessary conditions for the brain to repair and grow itself. This might be the neurobiological foundation for why our thoughts can feel clearer after a period of quiet reflection. Stillness also appears to be a catalyst for creativity. Many of our best ideas arrive not when we are staring intently at a problem, but when we step away. During these moments of mental quiet, the brain can form novel connections between disparate ideas, leading to leaps of insight. However, it is crucial to note that these practices are not a universal panacea. For some individuals, particularly those with a history of trauma or PTSD, attempting to force stillness can be counterproductive. It can trigger states of hypervigilance, a dissociative freeze response, or an amplification of intrusive thoughts. This does not invalidate the benefits of stillness, but it is a critical reminder that our inner worlds are complex. An approach that does not account for an individual's history may not be beneficial. For these individuals, guided practices or movement-based stillness might be more appropriate. What modern neuroscience is now revealing with fMRI scans is a truth that has been at the core of contemplative traditions for thousands of years. We are not the first culture to feel overwhelmed by chaos. We are simply the first to be able to measure its antidote with such precision. The ancient Stoic philosophers sought a state they called ataraxia, a robust tranquility, free from emotional disturbance. They believed strength came not from controlling external events, but from mastering one's inner response to them, a practice of cognitive stillness. In the East, Taoist philosophy is centered on the concept of wu wei, often translated as effortless action. It means acting in harmony with the natural flow of things, where action arises from a place of deep inner quiet and intuition, rather than from frantic effort. Buddhism, for over 2,500 years, has been a systematic exploration of the mind, with stillness at its heart. The goal of meditation is to cultivate a state of non-judgmental awareness, to observe the mind's chaotic state without being swept away by it. This ancient practice is a direct method for calming the DMN and reducing the body's stress response, outcomes now being validated by modern science. These traditions, separated by centuries, all arrived at the same fundamental conclusion. The world is chaotic, but within us lies the capacity to cultivate a core of stillness. What they described with metaphor, we now describe with neuroscience. But the essential truth remains unchanged. Understanding the paradox is the first step. Actively using it is the next. In a world of constant notifications, stillness must be deliberately cultivated. These are not just relaxation tips, they are targeted neurological interventions. Technique 1. The 2-minute neurological reset. Based on the finding that even brief silence can be physiologically calming, this is a practical tool for moments of overwhelm. Find a relatively quiet space. Set a timer for 2 minutes. This provides a defined container for the practice. Close your eyes and simply sit in the silence. Your only job is to notice the absence of noise. When the timer goes off, you are done. In these 2 minutes, you are giving your nervous system a chance to activate its parasympathetic, rest and repair, mode. It is a hard reboot for a stressed system. Technique 2. Box breathing. This technique is known for its use in high-stress environments because it directly influences the autonomic nervous system by stimulating the vagus nerve. Inhale slowly through your nose for a count of 4. Hold your breath for a count of 4. The slight increase in carbon dioxide signals your brain to calm down. Exhale slowly through your mouth for a count of 4. Hold your breath at the bottom for a count of 4. Repeat this cycle for 5 to 10 repetitions. This is a direct, physiological intervention to short-circuit the anxiety response. Technique 3. The art of the deliberate pause. The most profound way to integrate stillness is to weave micro-doses of it into the fabric of your day. The threshold pause. **** every time you walk through a doorway. Use it as a trigger to take one conscious breath. The send button pause. ***, before sending an email or text, take a few deep breaths. This creates a buffer between impulse and action. The sensory anchor. ***, several times a day, pause. Name 3 things you can see, 2 things you can hear, and 1 thing you can feel. This pulls you out of internal chatter and anchors you in the present moment. These are not just moments of rest. They are small, deliberate acts of rebellion against the tyranny of constant motion. We began with a single observation: that the feeling of stillness is an illusion. You are riding a torrent of unimaginable motion. The ground beneath you is not solid, and the space around you is not empty. The universe is a relentless storm. But we have discovered an even more profound truth. The human mind did not evolve to be a perfect mirror of this reality. It evolved to be a sanctuary from it. Your brain constructs a perception of stillness not out of ignorance, but out of necessity. It builds a psychological anchor so that you are not swept away. It creates a quiet space so that thought, creativity, and self-awareness can flourish. This is the stillness paradox. The physical world roars with constant motion, but the mind survives and thrives by learning how to be still. It's a paradox that lives in the pause between your heartbeats and in the silence that may allow new brain cells to grow. It is written in ancient philosophies and confirmed by modern science. The modern world is an expert at stealing this stillness. It tricks us into believing that being busy is the same as being productive. But the lesson of the paradox is clear. True strength and clarity are not found by speeding up, but by learning to access the eye of the hurricane you can create within yourself. The universe will never stop moving. The chaos is a given. But your ability to find and cultivate moments of inner stillness is not. That is a choice. And it is the secret to finding peace, right in the middle of it all. Stop, for a moment. Feel the stillness, the sense of unwavering calm. The floor beneath you is solid. The world outside is stable. You exist at the center of a quiet, unmoving universe. This feeling is so fundamental to our experience we never think to question it. But this feeling of stillness is an illusion. In this moment, you are not at rest. You, this planet, and everything you have ever known are hurtling through the void on an epic, unseen journey. A journey at a speed that defies intuition. Right now, you are moving at over 1,000,000 miles per hour. It sounds impossible. It feels wrong. How could you be moving at such a velocity and not feel a thing? Where are we going? And what engines are driving this voyage? This is a journey through the hidden layers of motion that define our existence. We will begin with the familiar ground beneath our feet and expand our frame of reference outward, step by step. From the planet to the solar system, from the galaxy to the fabric of the universe itself. With each step, the speed will accumulate, and the scale will expand. By the end, the comforting illusion of stillness will be replaced by a profound truth. To exist is to be in motion. To be alive is to be on a journey. And nothing in the entire universe is ever truly standing still. Our journey begins with the Earth. We think of it as solid, immovable. A foundation, but it is a spinning top. From its formation over 4.5 billion years ago, our planet has been rotating on its axis. Right now, it is turning, carrying us along with it. The speed of this rotation is not trivial. If you are near the equator, you are being carried in a vast circle at approximately 1,040 miles per hour. To put that into perspective, that is faster than the speed of sound. It is more than twice the cruising speed of a passenger jet. This speed is not the same for everyone. Earth's rotational velocity depends on your latitude. Much like a point on the outer edge of a vinyl record, someone at the equator travels the full 24,901 miles circumference of the Earth in about 24 hours. But if you were to stand at the North or South Pole, you would simply spin in a tight circle. For those in mid-latitudes, your speed is a more modest, but still impressive, 700 to 800 miles per hour. This raises a question. If we are all moving at hundreds, or even 1,000, miles per hour, why can't we feel it? The answer lies in a principle formalized by Newton: inertia and relative motion. You don't feel motion if that motion is constant. You only feel changes in motion, acceleration, deceleration, or a change in direction. Think about being on an airplane. During takeoff, you feel the acceleration. But when the plane reaches a constant cruising speed, the sensation of motion vanishes. The air inside the cabin is moving with you. Everything within your frame of reference is moving together. So, relative to you, nothing seems to be moving at all. The Earth is our planet-sized airplane. It spins at a stable and constant rate. And crucially, everything on it, the ground, the oceans, and the very atmosphere we breathe, is being carried along at the same constant speed. We are inside the cabin. Because the air moves with us, we don't feel a planetary wind. Because the ground moves with us, we can jump up and land in the same spot. Gravity also plays a crucial role. It pins us and the atmosphere firmly to the surface. The outward flinging force from the rotation is incredibly weak in comparison. Less than 1% of gravity's pull. So, our first layer of motion is a silent ride on a planetary carousel. A constant, supersonic spin we are adapted to ignore. But this is only the beginning. The Earth is not the center of the universe. It is held in place by the Sun's immense gravitational pull, locked in a constant, high-speed journey around it. This is the second, much faster, layer of our hidden motion. Our planet travels along a vast, almost circular path called an orbit. The total length of this path is a staggering 584 million miles. To complete this circuit in 1 year, the Earth has to be moving incredibly fast. And it is. Right now, the entire planet is hurtling through space, orbiting the Sun at an average speed of 67,000 miles per hour. That's about 18.5 miles per second. At that speed, you could travel from New York to Los Angeles in about 2.5 minutes. The planet's orbital speed is fast enough to cover a distance equal to its own diameter in just 7 minutes. This motion is, once again, completely imperceptible. The reason is the constancy of the motion and our shared frame of reference. The Earth is in a state of continuous free fall around the Sun. Gravity provides the smooth, constant acceleration that bends our path into an orbit, but with no sudden changes in speed. We, and everything on our planet, are pulled along on this journey together. This is where things get interesting. The Earth's spin and its orbit are not perfectly aligned. At different times of the day, these two speeds can add together or partially cancel each other out. At midnight, on the side of the Earth facing away from the Sun, the direction of surface rotation is the same as the direction of Earth's orbit. The two speeds add together. Your 1,040 miles per hour spin plus your 67,000 miles per hour orbit for a combined speed of 68,040 miles per hour. But 12 hours later, at noon, the direction of the planet's spin is opposite to its orbit. The rotational speed now subtracts from the orbital speed, 67,000 minus 1,040, or 65,960 miles per hour. So, every day, your personal speed through the solar system fluctuates by about 2,000 miles per hour, without you ever noticing. We are now passengers on spaceship Earth, a colossal vehicle on a perpetual, high-speed lap around its star. But our journey doesn't stop here. The Sun, and our entire solar system with it, is also on an even grander and faster journey. Our frame of reference is about to expand. We have gone from the Earth to the solar system. Now, we must zoom out further, to the scale of our home galaxy, the Milky Way. The Milky Way is an immense, rotating spiral of stars, gas, and dust, and our Sun is just one of its billions of citizens. And just as the Earth orbits the Sun itself orbits the supermassive black hole at the gravitational heart of our galaxy. Our entire solar system is being dragged along on an enormous orbital path. The scale of this journey is almost beyond comprehension. It takes our Sun approximately 225 to 250 million years to complete a single orbit of the Milky Way. This is a galactic year. The last time our solar system was in its current position, dinosaurs were just beginning to walk the Earth. All of recorded human history has taken place in a tiny fraction of this single cosmic lap. To cover such an immense distance, even over 250 million years, requires an unbelievable speed. The speed of our solar system as it orbits the galactic center is mind-boggling. We are traveling at an average speed of about 514,000 miles per hour, or 230 kilometers per second. Let's recalibrate. We started at roughly 1,000 miles per hour from Earth's spin. We added the 67,000 miles per hour of Earth's orbit. Now, we are layering on a speed of over 500,000 miles per hour. And once again, we are faced with the same question. Why are we not flung out into the void? The answer is the same, just on a galactic scale. The immense gravitational pull of the galaxy's combined mass holds our Sun and all the other stars in its grip. We are in a state of stable, continuous free fall around the galactic core. Our solar system isn't just moving in a flat circle. It also bobs up and down through the galactic plane, like a horse on a carousel. A journey that takes about 60 to 70 million years to complete. So now, our picture of motion has become incredibly complex. You are on a planet that is spinning. That planet is orbiting a star. That star is orbiting the center of a galaxy, all while bobbing up and down. And yet, the journey is still not over. The Milky Way itself is also hurtling through the universe. We must now take our final, and largest, leap in scale, to galaxy clusters, superclusters, and the entire observable universe. Even at this scale, there is no stillness. Our Milky Way galaxy is part of a gravitationally bound collection of over 50 galaxies known as the Local Group. Within this group, our Milky Way and our largest neighbor, the Andromeda Galaxy, are moving towards each other. Driven by gravity, we are on a collision course at a speed of roughly 250,000 miles per hour, about 110 kilometers per second, set to merge in about 4.5 billion years. But this is a local movement. There is a much larger motion at play. How do we measure the speed of our entire galaxy through intergalactic space? What can we measure it against? It turns out, there is a universal backdrop. It's not made of objects, but of energy. A faint glow of radiation that fills the entire universe. It's called the cosmic microwave background, or CMB. This is the echo of the Big Bang, the leftover heat from the creation of the universe. This ancient light is remarkably uniform, but not perfectly so. The CMB is slightly warmer, its light blue shifted in one direction, and slightly cooler, its light red shifted in the opposite direction. This is the cosmic Doppler effect. By measuring this shift, we can calculate our motion relative to the rest frame of the entire observable universe. And when we do, we get the most staggering speed yet. The Milky Way galaxy, and our local group with it, is rocketing through the universe at approximately 1.3 million miles per hour, about 600 kilometers per second. This motion is directed towards a massive concentration of galaxies known as the Virgo cluster and an even larger structure called the Great Attractor. So let's put it all together. You are on a planet spinning at up to 1040 miles per hour. You are in a solar system orbiting the galaxy at about 514,000 miles per hour. And you are in a galaxy flying through the universe at 1.3 million miles per hour. These motions all point in different directions. They are vectors in three-dimensional space. However, the speed of our galaxy relative to the CMB is by far the largest component. Our total, net speed through the universe, measured against the afterglow of creation, is dominated by this galactic motion, culminating in a velocity well over 1 million miles per hour. Every hour, you travel more than 1 million miles from where you were. And the entire time, you feel absolutely still. Our journey has been one of ever-expanding outward scales. But the illusion of stillness is just as profoundly shattered when we turn our gaze inward. The chair you are sitting on, the floor beneath you, the cells of your body, they all appear stable. But this, too, is an illusion. Everything you think of as solid is a seething frenzy of activity. All matter is made of atoms, and atoms are never still. They are in a state of constant, chaotic motion. The temperature of an object is a measure of the average kinetic energy of its atoms, how fast they are jiggling and vibrating. In a solid object, atoms are locked into a crystal lattice, but they vibrate furiously in place. The solidity of an object is the coherence of this collective vibration. One might imagine that at absolute zero, minus 273.15 degrees Celsius, all this atomic motion would cease. At this temperature, all thermal energy is gone. Surely, then, things would finally be still. The answer is no. Even at absolute zero, atoms still vibrate. This residual motion is a consequence of quantum mechanics, called zero-point energy. It is the minimum possible energy a quantum system can possess. The universe, at its most fundamental level, does not allow for perfect stillness. To be perfectly still, a particle would need to have both a precise, fixed position and zero momentum. But this is forbidden by one of the bedrock principles of the quantum world, Heisenberg's uncertainty principle. There is one final layer to our journey. We have talked about the motion of objects through space. But what about the motion of space itself? In the 1920s, astronomer Edwin Hubble discovered that almost all galaxies were moving away from us. And the farther away a galaxy was, the faster it was moving away. This did not mean we were at the center of a cosmic explosion. The interpretation is more subtle. The very fabric of space itself is expanding. The classic analogy is a loaf of raisin bread. As the dough expands, every raisin moves away from every other raisin. A raisin twice as far away appears to be moving away twice as fast. This is what we see with galaxies. They are not flying through space away from us. They are being carried along by the expansion of space itself. This adds a final, reality-altering twist. If you look far enough out, the cumulative expansion of space can cause a distant galaxy to recede from us faster than the speed of light. This doesn't violate Einstein's theory that nothing can travel through space faster than light. Here, it is space itself that is stretching. This cosmic expansion means there is no ultimate, fixed reference frame. Everything is moving away from everything else. The very ground of being is not static. It is dynamic. You are a passenger on spaceship Earth, orbiting a star in a galaxy that is sprinting through the cosmos, all while the very stage on which this grand drama unfolds is itself expanding in all directions. Let us return to where we began. To that feeling of quiet stillness. That feeling is a lie. An elegant and necessary lie, but a lie nonetheless. An illusion crafted by our brains for survival. We evolved on a surface where, for all practical purposes, the ground is stationary relative to us. Our senses are built to navigate this local, shared frame of reference, not to perceive the silent rush of our cosmic voyage. But the truth is, you are never still. To exist is to move. You are a participant in a multi-layered cosmic ballet. You spin with the daily rotation of the Earth. You waltz in a yearly orbit around the Sun. You are carried in a grand arc around the heart of the Milky Way. And your entire galaxy is part of an epic, 1.3 million mile/hour sprint across the expanding canvas of the universe. And this is just the motion of your center of mass. Within you, every atom is a vibrating frenzy. Every particle, a cloud of probability that never ceases. Stillness is not the default state of the universe. Motion is. Change is. The universe is not a static object. It is a dynamic event, a process of flow, energy, and relentless movement. The next time you sit quietly, feeling perfectly at rest, remember the truth. Remember the dizzying stack of velocities carrying you through the cosmos. You are not just sitting in a room. You are a traveler on the most spectacular journey imaginable. You are moving at 1.3 million miles/hour, and you are a part of the magnificent, perpetual motion that is the universe itself.